First speaker, Peter Ashwin from the University of Exeter, and his title is on his first slide.
Okay, great. Good morning, everyone. I said I would talk a bit about non-autonomous systems, and in particular, attractors and physical measures for non-autonomous systems, in the particular case where you have autonomous limits. And we've heard a little bit already about random dynamical systems in a couple of the talks, and non-autonomous systems are a bit like that, but with potentially less structure. So they're even more difficult to say anything other than quite general nonsense. And I'm going to try and convince you that there are some interesting questions there that I've been working on with some collaborators, but I think I need help from people who are much more familiar with the methods to actually get really good progress on these. So I'm very happy to sort of put some questions out there and hope that I'll get some response. So I'll talk a little bit about instabilities of non-autonomous systems generally, and in particular, there's a particular type of non-autonomous system that I've been studying in a variety of contexts in what we call parameter shifts. So these are parameterized families of autonomous systems, but the parameter changes. However, it limits to some sort of some constant values in the forwards and backwards time. A lot of work there has been done really on quite simple attracting cases, in particular equilibria. I'm not going to talk about that much because when chaotic or less trivial attractors appear in the limits, you can get new effects. So I'll talk a little bit about some work that I did with a student a couple of years ago on weak tracking and strong tracking of pullback attractors. Then I'll get on to non-autonomous physical measures, some fairly weak results on, I'd say, existence of non-autonomous physical measures, and then some consequences, some applications, and a discussion. Actually, should I? Everyone can hear me, right? Good, good. So the sort of systems I'm interested in are typically differential equations of the form x dot is f of x and some parameterized time-dependent parameter. So this is the non-autonomous system I'm particularly interested in. Of course, I'm most interested to relate that to what we call the frozen system. So the same thing, but I'll change the time dependence just for a constant. And one would hope that these autonomous systems, it's like a sort of set of bifurcation problems, will tell you something about the non-autonomous system, at least in the case where we have a parameter in here, this rate parameter R. When that is small, then effectively we're doing quasi-static variation, slow passage through bifurcations, that sort of thing. So this has been studied for many years. In particular, we're interested in what happens when R is not small. How does it break down? So you can think of this as the problem of adiabatic reduction of such systems. How do you work out how far you can push R and you still get something sensible? And what happens when it's really large? What sort of transitions you get? And this is effects we call rate-induced tipping in particular. So what happens if this system has chaotic attractors for certain values of the parameter? So we've got a parameter path, which is this sort of lambda, and we've got the rate, and these how we choose to go along the path and how fast should it affect what we get. And here's a sort of a motivating example, actually, this is from work with Bastiaanse and von der Heydt, looking at a relatively simple climate model, not totally simple in that it's multiple time scale. And it shows we start off with the system in some state here. There's some chaotic variability in it. And we increase the forcing. This is like a global temperature model for a period of 75 years. And then we reduce it back. So this is modeling in particular quadrupling for 75 years and then back to original. And in trying to understand how such climate models respond, the usual thing to do is you don't do just one run, you do a whole ensemble of runs. And for this particular choice of parameters, you find that the black lines, which are the ensemble, they sort of hang around here. And then when you turn off the CO2 at 75 years, there's actually quite a clear separation of the ensemble members. So some of them go up to some sort of hothouse state, some go back to some sort of temperate state. And if you, again, the common thing to do is you do an ensemble and then you do an ensemble average, which does something like this. And of course, the ensemble average is doing nothing of relevance to any of the ensemble members. There's actually, we've ended up with a very strongly bimodal distribution in the end. And so one of the things that we're trying to do is to say, actually, is there a rational reason for looking at this distribution? And what are the consequences of that in the future? So I'll start off with I'll give you some details of a numerical example. This is a double scroll circuit, which is introduced by Chua many years ago. It's a three-dimensional ODE, cubic nonlinearity, and we're choosing parameters where we have a bistability between two attractors. In fact, we find it very difficult to find any examples of model systems where you have both bistability and chaos. Sort of Lorenz, Rössler, typically, they've just got one attractor and they're chaotic. Other ones which are bistable, well, you can construct them, of course, but this one comes with two attractors built in. And just to give you a bit of a picture of the geometry, here's a little animation that shows the attractors. So if you start around here, you end up attracted to this little double scroll attractor. If you start a bit further out, then you're attracted to a large amplitude periodic orbit shown in the black. And the red is showing the stable manifold of a saddle periodic orbit. So there's a saddle periodic orbit that's sort of sitting in the red tube. And the unstable manifold of that is sort of represented by the cyan trajectory spiraling out. So this is a nice clean system. You've got two attractors. Everything's bounded. Nothing goes off to infinity. Yes, if you start it in particular for small initial conditions, which is what happens, this is actually a model of electronic circuit. You turn it on, then actually it settles into this chaotic attractor quite nicely and repeatably. But if you give it a big bump, then you get these large amplitude oscillations coming out of it. So what do we do with this? Well, we apply a parameter shift in phase space to this. So F, this is the double scroll system. This is 3 in 3D. And what we do is we apply a change in coordinate system that's just a linear shift in where all of the attractors live, if you like. So for the minus the time t minus infinity, then this is just the Chua double scroll system. For t is plus infinity, it's shifted by an amount sigma in some particular direction. So you've got limiting systems. So in the limit, in the large rate limit, then actually you can see this as a sudden switch from one system to the other. And sort of what's going to happen here, you can get the picture fairly clearly that if I start on this attractor and I shift a bit, if I shift just the right amount, I may end up with some of this attractor inside the tube and some outside, and that will give a partition of the measure on this so that some ends up in one limit and some in the other. Okay. But if we run this rate down to a very small value, we get what we call tracking. So you get the Chua double scroll attractor is presumably asymptotically stable. So if you do small enough perturbations, small enough tracking, what will happen is you will just follow it. And this is showing an ensemble of trajectories, and we start them in the basin of the pass limit attractor at some time, some -40 in this case, and they're all shown in different colors. So all you see is a sort of a multicolored tube of many trajectories. I don't know, there's a few hundred trajectories here. And this is showing the 3 different components. So if you see, there's a settling down at the beginning, and then you track very nicely the motion of the attractor. If I increase the rate, so this is the same amount of shift is done, you can see we get to this state of partial tipping, where the same thing is happening up to a certain point, and then after that, you can see there's there's a separation in the ensemble, that some of them go to a large amplitude, but some of them are still tracking along where the previous one is. And for yet higher rates, we can see there's actually you end up entirely outside the basin of the chaotic attractor. So this is like what happens in the large rate limit. But note that there's something interesting happening here, that there is some memory of the phase at which you tip. So there's no decay of correlations for this periodic attractor, of course. So how do we understand this in terms of a non-autonomous system? Well, we'll write the solution as a process of this form. So we've got 2 times now. We've got the starting time. If we start at x of s is x0, and we run forwards to a time t, then this is some process, and if we imagine this is parameterized by r and of course the f and lambda, but we'll keep the r dependence sort of explicit in the process, and we'll have a parameter shift that goes between the 2 limiting systems. Of course, if in the case of the frozen system, you can write the solution as a flow for a fixed lambda. And so this is some work with Hassan Al-Qayoun, a PhD student a couple of years ago, where we noted that if you start at any asymptotically stable attractor for the pass limit system, there will be a local pullback attractor whose upper backward limit is contained in A minus. Sorry, I put too many H's into Hassan's name. And we can construct the pullback attractor in this way. So you take a small neighborhood of the attractor at -infinity, and then you run it forwards from increasingly far times in the past. I mean, that's one of the issues with dealing with non-autonomous attractors, is that you have a choice usually. You either can keep the basin in focus, and so that would be a forward limit, and you lose much control over what the attractor looks like because it's a sort of a non-autonomous, it's a time-dependent set, or you keep the attractor in focus and then you lose control over what the basin looks like. That's a pullback case. And if we're talking about attractors and you want to keep the attractors in focus, then pullback is the way to go. Okay, so what about tracking? In the case where you have very nice properties, a stable branch, so you have an attractor uniformly exponentially stable, so such as, for example, the case for the double scroll, where we're doing really quite a simple type of time-dependent perturbation. We're just translating it in space. Then there basically we will get a branch that we can track for sufficiently small r. And what's more, you limit to there's a corresponding single attractor in the future limit that you will end up at. But it's not guaranteed for large enough values of r, and you can get these various rate-induced transitions of partial or total tipping. So I just want to spend a few minutes talking about something that, again, Hassan did in his thesis on noting that already even if you have a simple attractor in the past and a complex attractor in the future, there are different types of tracking that can appear. So in particular, if we look at the pullback attractor starting at some sort of rooted at some attractor A minus in the past, if that limits to the whole of the branch of the attractor in the branch in the future, we call that strong tracking, but it may actually limit to a subset. And here's an example, a parameter shifted Rossler system. So we'll shift smoothly A of t from some A minus to A plus. In A minus, we'll have a hyperbolic stable equilibrium, and A plus will have a chaotic attractor. And so there will be a pullback attracting solution. The complexity of that is determined just by what's happening in the past limit. So the fact that we're heading towards something more complex is just picked up by the fact that there's only one way we can approach that. There's only one trajectory, if you like. So what we would expect is for a typical trajectory, so this is now starting, this is some fixed value of r. In the past, we limit to the stable equilibrium. In the future, we should limit to some chaotic behavior. But for this particular value of r, we don't. And for another value of r, we don't. So actually, for typical values of r, you find you limit to something that looks like you're exploring the whole of the Rossler. But of course, the reason for that is you can get stuck on stable manifolds of unstable periodic orbits in the future limit system. So this is sort of trying to determine that. We start at Z minus and undertake the parameter shift. We'll end up, it looks like we've got a two-dimensional unstable manifold. Actually, it's one-dimensional. There's a rather complex set of bifurcations going on there. At different times, if we look at the gap between the end point on some section and this unstable periodic orbit, so this is showing this as a function of r. So for small, we find, these are at progressive times in the future. So we'll find that here we're actually settling down to an unstable periodic orbit at this particular rate. There are additional routes that appear in this curve as t increases, which correspond to going around many times before you approach. Of course, this is a bit of a simplification in that this is a two-dimensional section, and I'm just drawing one coordinate here, but the attraction in the vertical direction is really quite strong. So there's no rigorous justification of this, I should say. This is a sort of numerical observations. But notice we end up with actually a dense set of values of the rate where we have connections that go from this equilibrium in the past to a periodic orbit in the future in some sort of, if you extend the system and you compactify it. Okay. Yeah, so non-autonomous physical measures. So what is our working definition for a physical measure? Well, let's start off with autonomous ones. So an empirical measure starting at some point x0, running forwards at some time t. This is, if you like, a delta function smeared out along the orbit. So it's defined in this way. And then an attractor A for an autonomous system with a basin of attraction B. A physical measure is some probability measure supported on A, such that for Lebesgue almost every x in the basin, you converge, the empirical measure converges weakly to mu. Now, there's a problem with using that directly in a non-autonomous system, in that if you start to take sections in the far past, you don't want the definition of your non-autonomous physical measure to actually depend on exactly the details of that. And so if you have lack of decay of correlations, that will cause a problem. And so actually in the again, this is in the autonomous setting, we'll call it an attracting measure if it's a physical measure, such that for every probability measure, nu 0, absolutely continuous with respect to Lebesgue and supported within the basin, then this is attracted, this converges weakly to mu. So let's now consider this. We're always doing this relative to an asymptotically autonomous system that will have a local attractor A minus and basin B minus in the past limit, and a pullback attractor starting at attractor A minus. So this is a non-autonomous invariant set such that this set is bounded, and on each fiber it's closed. And you've got there is basically a U bar. I think that should be U bar in there. For small enough neighborhoods of A minus that are contained in B minus, you actually get attracted in the pullback sense to A of t. Sorry, that should be not a curly A. And then on non-autonomous empirical measure, well, we got 2 times here. So we started a time tau minus t, and we run to a time tau. Sorry, I think I've switched the order of the times here as well. So given an attractor A minus, a physical measure on this non-autonomous attractor is a measure that is supported on A of t for each t, and for Lebesgue almost every x0, the empirical measure converges weakly to mu of t. So in this paper that appeared this year, we give sufficient conditions on a scenario such that pullback attracting measures, physical measures exist. So a pullback attracting measure is going to be that actually not just points are attracted, but actually probability measures of smooth density supported within the basin converge to the measure at time t. So we give sufficient conditions that these can exist, and basically we need two properties. We need some sort of mixing properties in the past limit measure so that the physical measure is attracting other absolutely continuous measures, and exponential convergence of various properties of these measures and their support in the limit t goes to infinity. Okay, so in the existence, this is just briefly highlighting what we've done here. The existence of these measures in this paper, we start in the autonomous setting, and we're considering the what the flow induces on Borel probability measures, and in that sense, so mu is an attracting measure of the past limit system if there's a neighborhood U such that every Lebesgue absolutely continuous probability measure is attracted to mu under this this operation. And it's a physical measure if the past limit system, if there's a neighborhood such that Lebesgue almost all for x, delta x is attracted to mu under this this flow on probability measures. So suppose you got mu is an attracting measure in the past limit system. We want to say something about a non-autonomous measure, mu t. We'll call it an attracting measure rooted at mu if, well, there's a neighborhood such that for every Lebesgue absolute continuous probability measure lambda that is supported on this neighborhood, this is pullback attracted to mu of t. So this is quite a strong assumption. And a physical measure rooted at mu means that there's a neighborhood such that your delta x is pullback Cesaro attracted to mu of t. So this is in the mean, so the mean of this thing under Cesaro averages. So suppose that now we want to try and relate this to measures of the autonomous systems, the frozen systems for different values of lambda. And this is a result that says, okay, we've got a family of invariant measures for the frozen systems. These have support Q of lambda. And let's suppose that these limit to an attracting measure with some support P in the as we go t to minus infinity. And then this result is saying that we need sufficiently fast convergence both of the parameterized family of invariant measures and of their supports. Then we get a measure, a non-autonomous measure that's pullback attracted to such that mu is pullback attracted to mu of t. Hang on, yes. So this is the past limit measure, and so this is pullback attracted. This is like a minimum of what you want, and then under additional assumptions on closeness, sort of exponential closeness of the approach of the vector field and Lyapunov stability, then we'll get an attracting measure of the past. If mu is an attracting measure of the past limit system, then this non-autonomous system will be an attracting measure rooted at mu for the non-autonomous system. And the proof that's in the paper uses a couple of concepts that have been developed by Julian Newman, who's the main author on this, and a postdoc working with me. So he's got basically a system of bounds, exponential bounds on a variety of norms and monotone-like non-autonomousness controller. I tried to dissuade him from using that, but he really likes it. So and a growth controller of different rates that will give you the desired estimates. So this is independent. So this first result doesn't require that actually mu is an attractor itself. It's just saying that you have one particular measure that's attracted in the pullback sense. To get the actual attracting measure result, then we're using estimates in neighborhoods of the attractor at the past limit. So I'd now like to return to the question of what's happening in the examples that I showed at the beginning of this separation of the ensemble. How do we understand that using a non-autonomous physical measure? So if you have a number of past and future attractors, then these physical measures should allow us to understand, to actually denote, to give a notion of probability of tipping from the outcome going from one to different attractors. And so let's consider just one attractor in the past and a physical measure on this attractor. And we've got a non-autonomous system that starts at A minus, and there's a physical measure on this pullback attractor. And let's suppose we have several disjoint attractors in the future with various basins of attraction that exhaust Lebesgue measure. So we're going to a different landscape, and we've got Lyapunov stability, and we've got some assumptions over physical measure not getting caught on the boundaries and disappearing down sort of sets of zero Lebesgue measure in the future. Then under these assumptions, we can actually define a probability of tipping from one attractor into a number of possible outcomes simply by looking at the basin of the future attractor, the jth future attractor, as t goes to infinity in the measure, in this non-autonomous measure. So this exists under the assumptions above, and what's more, the probability sum to 1. And this is a computable thing. As we change R, as we change the rate, so this is for one particular shift, parameter shift in the double scroll that takes you to a value where you don't get total tipping even for infinite R. And these are sort of numerical estimates with standard error bounds. And you can see for small enough R, we're tracking. For large enough R, we've got some sort of consistent partial tipping where about 20% go into the limit cycle and about 80% remain on the chaotic attractor. For a larger shift, we end up with total tipping here. And so there's actually apparently a monotonic change in the P, in the probability of tipping here. Geometrically, we can also see what's going on here. So these are now for the double scroll system. This is showing, which is a three-dimensional differential equation. This is a slice through phase space at some x1 is 0, showing x2 against x3. This is some time, let's see, t is minus 20. So this is before the parameter shift happens. And this is showing the basin of attraction for the future chaotic attractor, where the yellow corresponds to the big limit cycle, the blue corresponds to the chaotic attractor, the bounded chaotic attractor. And you can see, actually, maybe it's easier to understand it from this side. At time t equals 0, you're actually seeing a slightly deformed, slight deformation of this red tube, a slice through this red tube that I showed in the animation previously. But as time goes backwards, this red tube gets rather mixed up by the chaotic dynamics that's going on in the basin of attraction of the past limit attractor. as you go further back, it sort of spreads out and gets nicely mixed in. So this was at one very specific value of rate. So this is like different slices through the basin of attraction of the future limit attractor as time goes forwards. This is the slice through one very specific value of time, but now changing the rate at which we change things. So this is showing a case of a small rate at some time before the shift has happened. And what you can see here is there's a what seems to be a nice open set. The red dots show a section through the chaotic attractor, the double scroll attractor here. And you can see in this case, the past limit has a natural measure supported on the red set. And this is entirely contained within the blue region. And so everything here heads towards tracks in the limit going to infinity. These are larger values of R where you're no longer in the case of tracking. There's some partial tipping in both cases. And so in going to the right, there's an increasing probability of being on a trajectory for the natural measure that will actually tip. So the natural measures, if you like, they're different from the natural measures on autonomous systems in that the asymptotic behavior can be quite different. And that's the other thing in that generally working with attractors in non-autonomous systems. If you have an attractor in a pullback sense, there's absolutely no reason it needs to be an attractor in the future limit sense. In fact, it may converge to a repeller. And those cases are particularly interesting for understanding transitions in non-autonomous systems. And with Sebastian Wieczorek, we've been working on, in simpler cases, so non-chaotic cases, criteria for having that type of instability. So there's a number of challenges that I think I definitely need some help with to get a better theoretical understanding of what sort of, what's the right way to understand these physical measures on non-autonomous attractors. And in particular cases where this physical measure splits into the basin of several future attractors. To understand the thresholds and the edge states in the cases where it's splitting. If you have multi-scale chaotic systems, there are particular issues there. And I think one of the most interesting things is whether these insights can be used to improve the science of ensemble forecasts. And from talking to people doing these, it seems to be a bit of a black art that you tickle your initial conditions in various places to try and expand them out to a large enough set that will actually represent all the possible outcomes and give you reliable probabilities that certain outcomes will happen. But I think there's a lot to do there. I'd like to thank the sponsors. I've got some papers there where this is detailed. I'm very happy to talk to anyone after this. But also, is Matt here? Did he manage to get up? He might still be in. Yes, very good. Okay, I've got a little dedication to you. So everyone's using ChatGPT these days. So I asked ChatGPT to develop a little dedication to you in the style of William McGonagall. And yes, okay. So I'm happy to take any questions.
Late, but very interested in this topic. So one other problem that we have in climate is like when there is the emergence of maybe a new basin of attraction, right? And we have no clue about it.
how can we guess that we're going towards a new basin of attraction if we just observe a very short trajectory? It can be an extreme event that is like a freak event, like the Canada heat wave or the Emilia floods. So that I think it will be very beneficial to have some technique to say this is an event of at the edge of the current basin of attraction, or this is enabling us to see a trajectory that is already on the new basin of attraction enabled by climate change.
Yeah, well, I guess that's a very difficult problem, and there's certainly no easy answer to it. I mean, I hope that the idea of a non-autonomous physical measure could actually help. Well, one of the things you can easily observe is that the non-autonomous physical measure in these cases is not actually equal to the physical measure for the frozen system. So that already tells you something, that if you can be drifting off the attractor that you get in the frozen system, and the faster that you're changing, the more you can drift off. That doesn't necessarily help you, but it does to say that if you're doing sort of a lot of assumptions of stationarity, they could be really quite badly off. So yeah, I guess non-autonomous simulations and find the natural non-autonomous natural measure, but yeah.
If you done some study on the Lyapunov exponent, because when you have a non-autonomous system with respect to the frozen system without no forcing, you introduce another Lyapunov exponent in the system. Have you studied how change this Lyapunov exponent when you move the parameter? If have the opportunity to connect the dynamical behavior you observe with the change in the Lyapunov spectrum. You done this?
Well, I guess there are different, just as there are different notions of attraction, there are different notions of a Lyapunov exponent as well, depending on whether you're going forwards and backwards in time. So you can be on the same non-autonomous attractor, and your limit in the forwards time could be quite different from what it was in the backwards time. But it's not something I've looked at in detail. But yeah.
Further questions? Georg?
Yes, so I went to an interesting talk actually the other day from someone who was talking about, I think there were regional forecasts where I think the way they put it, they're trying to find the butterflies and sort of tickle them in their different regional areas, and through doing a lot of forecasts, you start to learn where the instabilities can develop, and so these are good places to actually take an ensemble, an initial ensemble that hopefully will converge quite rapidly to the full set of possible outcomes. But yeah.
Thank you very much. Thank you for the invitation. It's very nice to be here. So as George said yesterday, we're speaking roughly on the same topic, but I'm going to focus on a particular part. So the introduction will be kind of similar, not just in this talk, but in some other talks. But just to fix some ideas, we're interested in dynamical system, f going from x to x. Most of my examples will be interval maps, in fact. So invariant measure, invariant probability measure, mu, and observables, phi. So they're going into RD. I'm probably going to restrict to R1 just for purposes of exposition, but everything here works in RD. So in regimes where the CLT holds, so where if I normalize by square root n, I'll have to normalize the observable first, actually, but let me get to that. So this converges to, so of course I have to, distribution. So I'm assuming that the integral of phi d mu is equal to 0. And if not, then I can just subtract that value from phi to make that true. Okay, so in regimes where we have the CLT, so it converges to this normal distribution with this covariance matrix sigma, may hope to get a weak invariance principle. And we've already seen that a few times this week. So what I'm thinking there is I'm thinking about Sn of t. So t is some real number. And probably I'm going to take t between 0 and 1 actually, but k equals 0 up to nt minus 1 phi f to the k. So for this SNT, we might hope that Sn tends to W distribution where W is a Brownian motion. And I could pretend I can draw a Brownian motion, but I imagine your imaginations are better than my drawings. So this kind of setup has been studied by lots of people, including many people in the room, seen in many systems, many cases, systems, and e.g., I'm going to take the risk of naming some people, but in a very vague way. So I was going to list people who are here, but Mike's not here. Ian, Matt, who I particularly mark out because it's their birthday, and happy birthday to them. Turek, I mean, okay, this is going to go on forever, but Grizel, okay, some work of Mark Holland with Ian. Gary has done some things. Anyway, basically, many people in the audience, and if I haven't mentioned you, I apologize. Please feel included in this ... in a kind of a welcoming way, but I can't say everything. So the regime for the CLT, we can think of, or at least I can think of, and hopefully you can believe me, is that F is good and phi is good. So, I mean, F is sufficiently mixing, phi is sufficiently irregular. So, for example, well, let me talk about what bad means, just to give you an idea about that. So, yeah, if F is some kind of uniformly hyperbolic thing, phi is Hilda, then you kind of expect this kind of thing to happen. But you can go beyond that, of course. Okay, but if F is in some sense bad, so for example, I'm going to say very intermittent, or phi is bad, so e.g. not square integrable, then the CLT can fail. As I say, we've already seen this in some talks previously this week, but you might hope there can be some alternative scaling, can be suitable scaling to give you some stable law instead. So e.g., and there may be more sophisticated versions of this, but e.g. an equals n to the, I was going to write alpha, but do I want, oh, okay, alpha. Maybe n to the alpha times something slightly varying or something like that. but let's not worry about the details too much. You saw that in George's talk. K equals 0, n minus 1 phi f to the k. This converges to alpha stable. I'm going to continually worry that I've got the wrong signs on my alphas, but 1 over alpha, yeah, right. Okay, thank you. Okay, I'm not doing penance down here. I'm doing my shoelace up. Okay, thank you. Okay, so in that case, as we saw in various talks, for example, Georg's very nice talk with some nice pictures, you might hope to get, in this case, a Levy process. So I might hope to show that SNT normalized by this suitable normalization, k equals 0 and t minus 1. So same stuff. This converges, maybe, hopefully, to a Levy process. And here I feel obliged to try and draw something, but of course it'll be terrible. So this kind of picture, you've got something wiggly, and then you've got some jumps, something wiggly, some jumps. And I'm trying to draw this in a relevant space. So the space you might try and look at, and what George was talking about that Marta Tyran-Kaminska looked at, is in the case of D01. So this is a Cadillac space. So these are the paths from X going from 0, 1. And of course, I'm drawing it in R1, but in principle, it goes to RD. And these are Cadillac. So that means continuous on the right and limits on the left. So this is a full dot there and a holy dot there. Yeah, so you might hope to get a Levy process like that. So it makes sense at this point to try and introduce some kind of metric on this space to try and give you an idea about what we do that's different. Okay, so I'll introduce the metric, and then if you've got any questions, I'll stop and ask to see if you have them. So standard metric for convergence of these Levy processes is, well, one way you can think about it is this one. So you've got two paths, X and Y. So I'm thinking about this as a path, right? This is an X. You can look at the infimum over lambda, maximum over X composed with lambda minus Y. And here I'm using the subnorm. You don't necessarily have to use the subnorm, but some suitable norm. So what are these lambdas? These lambdas are time reparameterizations. Right, so they just, they preserve the order in 0, 1, but they can shuggle time along a little bit, to use a nice Scottish word. So for example, you might have something like this, but it goes a little bit beyond, and then it jumps up somewhere like that. And then it goes down somewhere like that. This green thing here is considered close because if I am allowed to do a time parameterization to move this dot essentially to there, and so that the jumps more or less line up. So because the time parameterization I need to do is just this tiny little bit here, that would feature in here, and that will be something small. And then the difference between the green line and the white line is essentially what you see here. So you're taking the maximum of those two. Okay, so you're allowed to just shuffle your green thing to sort of match your white thing or vice versa. And so they get close together. Okay, so that's J1. So this is J1 topology. J1 Skorod topology. Right, so as I said, and as remarked on George's mention of this, although without the right accents, Tyran-Kaminska possibly right spelling. Anyway, in 2010, gives conditions for this convergence. And so firstly, why do you get a Levy process? Well, again, as George mentioned yesterday, let's see, jumps. Here, when Tyra Kaminska was looking at this, she was looking at jumps caused by phi being bad. So the dynamics was generally in that paper thought of as being good. So nice decay of correlations. But the phi was bad. You have some heavy tail. You have some very large observations, which dominate all the previous ones, so that your sum really, as George was saying yesterday, your sum really sees the maximum rather than the whole sum, because one term just dominates everything so much. Anyway, and that's what causes these big jumps. Okay. So that's, yeah, due to very large observations. And to keep people who like intermittent things interested, this is not what Taryn Kaminska did, and she pointed out why that doesn't work. But we are interested also in the intermittent case where you get trapped in some region. So for example, if you think about the Malcolm map and you get trapped around 0, and if you see phi of 0 or something approximately equal to phi of 0 lots and lots of times, and that adds up, and that sort of behaves like a big jump as well. So this is something you will remember from Georg's talk yesterday, but I'll maybe mention more about that later. But this is adapting what I'm going to describe here to that is an ongoing project with Ian and Anna, Christina, and George. Okay, so that's a sort of standard kind of setting, and I'm going to move on to a less standard setting. But does anyone have any questions so far? Okay, right. So, as I say, the focus here is going to be on heavy tails. So that's where phi can have some really, really high values at some point. And so Taryn Kaminska allowed for having large values, but she wouldn't, her framework wouldn't allow clusters of large values. So that's what we're interested in. So here you get some kind of pure jump up there. As you saw in George's talk, you might get some kind of intermediate jumps. And this space just can't hold that, can't handle that. So George's talk was about how we encode that into point processes. Here I'm going to talk about how we put that into these Cadillac spaces, or these generalized Cadillac spaces. Okay, so let me give you an example. I'm not really going to give a theorem about anything in this talk, but I'm going to focus on an example. So the same dynamics as in George's talk, so 3x mod 1. So in here, mu is equal to big. And I'm going to let phi of x be equal to x minus an eighth to the minus 2 minus x minus 3/8 to the minus 2. Okay, so of course, what's happening here is that there are spikes at the periodic cycle an eighth, which goes to 3/8, which goes to an eighth, and so on. So it's a periodic cycle period 2. And so sometimes you get a very large positive jump, and sometimes you get a very large negative jump. Okay, and how they cluster is what we're interested in looking at. Okay, so I want to try and draw a picture now, which is fairly schematic, but such is life. We have some nice simulations like the one George showed yesterday in the paper, which is a preprint archive. So you can think about a bit of SN here. So Okay, so I'm assuming I have some big jump at time k over n. So I'm coming in from the left here, and then I'm having a big negative jump down. So here, so the time scale is along the bottom, t. So t is in 0, 1. So the time scale is down here. So I'm thinking about the jump that's happening at k over n. So I'm splitting up the 0, 1 into 1 over n, 2 over n, and so on. And so I have a big jump down there. It's k plus 1 over n. So what I'm doing is I'm hitting, not this, I'm hitting this. I'm getting very close to 3/8. And so suddenly I'm going down a lot. And then because I'm 3/8 is near to 1, well, it's going to map close to 1/8, I'm going to see this. So I'm going to go up, but not as much, right? Because it's a repelling periodic cycle. So I see, in this particular case, the first observation I see is going to be the worst one. But that's not the general case, but that's the case here. So I'm going to jump up a little bit. And then this is k plus 2 over n. And then I'm going to go down again. And it kind of settles down because I'm getting further and further away from this periodic orbit. And so I see less and less contribution from this phi as my iterates go on. So I kind of settle down to something like that. Okay, and so the idea is that, and this is not real because you can't fix one of these and take a limit, but the idea is sort of that when I see a pattern like this, then I'm gonna, n's gonna go to infinity, and so these jumps are gonna all line up instantaneously. So let me try and mirror it. So what I'm doing is I'm going, that's my sort of maximum range of jump, but then I go across like that, and then I'm going like that, and then I'm going down like that, and then I'm going up like that. So really, I'm going down, I'm going up, not up, I'm going up to that one, I'm going down to that one, I'm going up to that one, and then I'm kind of carrying on like that. Okay, so these jumps are all squashed into instantaneous time as n goes to infinity. And as I say, this is lying really, but a pattern like this is what happens. And so, of course, this thing here with all these dots, is not a Cadillac path anymore. So you have to do something to handle this. So in particular, this thing doesn't lie in D01. So and I'm lying here, but limit not in D01. So Witt, who has a very nice kind of fat book about these kinds of things, well, lots of kinds of things, but in the later chapters, he talks about a space E. And okay, so everything here, it does generalize to RD, but I'm just going to do everything in R1 because of my limitations as a drawer of pictures and the two-dimensional nature of the board. So take D equals 1 for X position. So what's this? So this is a space E, and my paths, well, my objects in there look like a triple X, SX, and I, S, S in SX. Okay, so these are the triples. So what's X? So X lies in D01. So this is a Cadillac path as before. These things here are, this contains the discontinuities. Of X, right? So these jumps. So it would contain this point, this time point here, this time point here, for example. And these, okay, I'm running out of space. These things here are in D equals 1 case, they are intervals containing at least this point and that point. Okay, so I can think about those as being xs, oops, xs minus and x of s. Right, so it contains at least this point here and this point here. So the interval I have to consider, it's going to be something like that, or just containing just spanning that. Not clear. Okay, so that's my space E. So it's this. It's like these Cadillac paths with these decorations at the jumps. Okay. So first thing to say is that you can. This is clearly a generalization of D01 because you can embed D01 in here quite straightforwardly. And let me explain how to do that because it'll be useful later. So if X is in D01, can embed into E by letting S be equal to the discontinuities and I of S just simply the interval x s minus x of s. Okay, so in this picture here, so I can it's just containing that interval between these two things here. Okay, right. Okay, so what's the natural distance here? Well, a natural distance is just the Hausdorff distance. So d e xy equals the Hausdorff distance. So just thinking about these paths as just sets and a distance between two sets. Okay, so let me try and put this into our example. So our example, so I'm trying to mirror this thing up there. So yeah, so I have this thing here. I jump down like that. I go up. I go down. Oops, no, go up. I go down. I kind of settle. And what I do is I add in these extra lines to embed myself in E. Okay, so it's no longer a graph, but it's still an object in R2. And as n tends to infinity, and again, I'm lying a bit here, but whenever you see a pattern like this, as n tends to infinity, what you end up with is your initial, well, this is going to be more wobbly than this really, but anyway, some kind of wobbly thing. And then you're going to get something that goes all the way down to the bottom of this range and then ends up roughly here. So, okay. So our new object is this thing here. So it's this thing here with the interval going all the way down to the maximum of the range of this excursion, but then sort of ending up roughly around here. Okay. So you can see now that it is possible for limits to exist in this space. So this space is richer and allows for these kinds of convergence. But there's some price. So we get convergence and a new piece of chalk. But what do we lose? We lose the size and the order of the jumps. Right, so here we saw a big jump here, followed by a relatively big jump, followed by a smaller jump, and so on. Whereas here, you don't see any of that. You just see that some jumping happened, but you don't record what that really was. You just record the range of the possible, the sort of convex hull of all the jumps. So that's suboptimal. So width also has a way of trying to solve one of these problems. So width space F is similar, but includes a time parameter, includes a time parameterization, which I can't write, parameterization. You see yesterday that George has beautiful handwriting, but gave a slide talk, whereas I don't have such great handwriting, but I apologize for that. Okay, so he had really great pictures, and I have bad pictures as well. Anyway, so what I'm saying, I'm saying that in this, it's a bit too spiky to see. Draw it again. In this thing here, we've got a path that goes like that. Oops. And a path that is less complicated. It just goes like that. So you can see that these two things, you don't even have to squash. These two things are close in E, because this span here is close to this span here. And I haven't explained what F is, but there's this time parameterization, which tells you kind of go down and then up and then down again. It records that, space F, so far apart in F. So F is more useful for recording the orders of your, I shouldn't use orders in terms of what happens in time, the orders of your fluctuations. So F has a time parameterization which will record the fact that you went up in the middle. Okay, so that makes it better, but still not good enough for us, because we want to see F doesn't see the heights of the intermediate jumps. Right, we're interested in these kind of big hops. This thing here, just you might have like several hops in here, and it wouldn't see those. It would just see that you went through some hops. For your application, you may not want that. You may not care. F might be enough for you, but for us, we wanted to be able to handle these sort of discrete jumps and record what they were. Okay. So before I introduce what we call F prime, I will have a sip of water and ask if there's any questions. Mm-hmm. Yes. Yes. Well, yeah, sort of. I basically I wanted to draw this infinitesimally small gap in time, but I couldn't do that. So yes, I'm thinking about this as being very narrow. Yeah. Thank you. Yeah. Yes. Yes. How do you find jump? I mean, you see it in this sum, right? Yeah. Well, hopefully you'll see that in the F prime. I hope that I'll answer that. I hope. Wouldn't I see? Yeah, you see the higher jumps in that. Yeah. Maybe misunderstood the question. Ah, sure. Yeah, what you do is, if you remember George's talk, there was a thing about taking some threshold epsilon above which you think about a jump as being a jump, and then you take your epsilon to 0, and it's some kind of limiting thing. So there is a way of handling that question. Yes, and there was a question in the back. Yes. This all works in RD. You can do multidimensional things as well, but please don't make me do that now. Okay, so I'm going to define F prime to be equal to another triple. So X, SX, And then I've got here as an excursion. So E for excursion. I guess E is a slightly dangerous letter to use, but there we are. So it's triple like that. So again, this is in D 0, 1. This contains the discontinuities of X. Now this is an excursion, and it's in another space, which is very similar to D. It's D tilde 0, 1. So D tilde 0, 1 is D 0, 1 with a kind of softer metric. So we don't care about the time period reparameterizations. All right, so it's a bit floppy, but it's very useful for our purposes. So you just take the infimum over the time parameterizations of this, rather than taking the infimum of that. Sorry, rather than taking the maximum of that and the distance between lambda and the identity. Okay, so it's basically time parameter free. So so this thing here. Let's get the dots in the wrong place. This thing here is the same as this thing here. So I just rescale everything. I shift this to there. Okay, so it's a floppier space, but it works nicely in our case. Well, and I think much more generally as well. Okay, so what do I need to do? I need to put a metric on this space. So I'm inheriting some metrics from the spaces I've already come up with. So what I want to do, so time parameterizations, reparameterizing time. Changes nothing. So it's an equivalence class up to time reparameterization. Okay, so I'm going to project these things into E. All right. So this is just X, SX, nothing changes. But now I replace this excursion. So you think about this as an element of D, right? It can go up and down. But what I'm going to do is I'm just going to take the range of it, basically. Take, it's not I of X, it's I of S, S in SX. Okay, so this is just, this is the span of EX S. So I guess I should just draw something quickly, but so I'm going like that, I'm going like that. So this is something in D, and then I'm attaching some excursion in here, which I can't really draw, but I attach an excursion which kind of goes up and down. Goes up and down, something, whatever. So I attach this at this point here. It's got to be much bigger than that, doesn't it? It's a bad picture. Okay, let's go like that. I attach something that goes. So this is my E. So this is my S. This is my E. How have I written it? EXS. So this is my element of D tilde. So I'm attaching this at this point here. So it's a decorated space. You've got D, an element of D with this excursion attached to it. And so I can project this thing into E by replacing this excursion here just with the span of the excursion. So I just replace this with an interval like that. So I put what I wanted was to put, oops. So the element in E looks like this. Okay, so I can project these things into E like that. Okay, and then I have a metric in E inherited from the Witt situation. Okay, that's the easier part. The harder part is to embed, well, what I want to do is I want to take X and these excursions here and put them all into one space together. So I'm going to take this X I'm going to cut open along the timeline at some corresponding points here. It makes sense that these will be at most countable. So I'm able to do that. So I cut the timeline open and I put these inside it. Okay, so whenever so what I do is I've deformed time. So what I end up with is an element of d tilde. Okay, so kind of wanted to draw a picture for that, but let's see. So yeah, maybe I can do the same thing here. So this element here with this decoration here. So I've drawn this green thing here. That's the projection into E, but the projection into d tilde of x, x bar, is equal to some x d tilde, where I say I open up gaps, time gaps, at s in sx, and insert the relevant excursion at that time gap. Okay, so here, the picture would be, I open up the gap here. So my S, same heights. So my S was here, and I open up a little bit of space here, and I put this one inside it. Maybe I'll just for, so I can draw the picture, I open up this much space. So I open up some space. What I ended up with, so if I ignore this open up space, what I've got is my original picture. But in this open up space, I plug this thing in. So let me draw that in a different color. So I plug in this, that. I had to go all the way up, didn't I? Otherwise that wouldn't make any sense. Sorry. This is going to go to there. So, oh, no, don't do that. That's fine. So, down. I've copied it wrong. Down. Okay, great. So I add this in. I don't know why I'm insisting on drawing these, but anyway. So this is my projection of this part of x into d tilde. Okay, so what have I lost? I've lost, because I've opened up this gap here, I've lost the time control that this one had. This told me there was a jump at this time. This one says, oh, there's some jumps in this area here. So you lose something. But it lives in d tilde, so we don't really care. So this somehow makes sense. So just to recap, I'm projecting firstly into E, replace all of these excursions just with a line in R1. I'm projecting into d tilde, so I replace, at every jump, I plug in this excursion here. And so now my metric on my space is just the following. Check I haven't missed anything. Yes. It does, but it's, well, yes and no. So it has a time information, but it's an equivalence class up to all time representation. So in that sense, no. It comes with the order of the jumps. The time of the jumps is not relevant. Yeah, so you lose something. Okay, so the metric is now dfx xy is equal to the minimum of the metric when you project into E, pi E y, and when you project into d tilde. Yeah, so yeah, that's the metric there. So that's the space. So the next thing I'm going to do is I'm going to just comment on how it compares to other spaces. So if you've looked at this stuff before, you've got M1 and M2 lurking in the background of your minds, I guess. So we can get convergence in F prime where convergence in other topologies isn't possible. So here I'm thinking about J1. So I mentioned this problem with clustering. Taryn Kaminster did a really good job in the case where you don't have clustering, but if you do have clustering, it doesn't work. So that's C above. You've got M1. You can't handle things that look like that in M1 or M2. I say can't handle. Yeah, I think so. So things that go like that. So overshoots. And moreover, we retain the information in the jumps. Okay, so I'm rubbing out the example now, but this is what I'm just going to talk about. So e.g., for our example, Sn is equal to 1 over Snt. 1 over, turns out that 16n squares is a natural normalization. K equals 0 to Nt minus 1 phi t to the k tends to V in F prime, where V is equal to V SV EV S S in SV. Sorry, it's round bracket. So V is a 1 over 2 Levy process. And at S in SV, my excursion looks something like the following, well, not something like this. My excursion looks like this. So it's equal to some constant, CS, times characteristic function. It doesn't matter what times I put in here. Going back to Mark's question just now, I could put any kind of summable sequence in here. 2 over 2 to the n. Minus, okay, erase all this. Minus CS over 3, characteristic function 2 over 2 to the n, 3 over 2 to the n, plus CS over 3 squared, 1, 3 over 2 to the n, 4 over 2 to the n, and so on. Okay, so in here, CS, you can just work it out. CS is equal to 4 over 3 VS minus VS minus the total jump, not total, the resulting jump in the end. So this thing here will fill the gap and actually go beyond the gap. Okay, and the proof of convergence goes via point processes. As in George's talk. And I think I'll stop there. Thank you for your attention.
Thank you very much. Maybe a question there.
Okay, do you think that's worth talking about now? Yeah.
You're building a threshold.
Yeah.
It's like when you want to prove the theorem, you're building the threshold. But the statement of the theorem and the definition of the spaces does not have an epsilon in it.
Correct.
So
Well,
and it-
the statement actually does. The statement has a. If you saw George's result yesterday, for the big VN,
no,
the
no,
endpoint
but
processes.
the statement about the theorem of the convergence of the processes
Correct. Correct.
does not have an epsilon in it.
Correct. Correct.
I mean, yes, you have lots of jumps. You have a dense set of jumps. Big deal. You just have lots of jumps. So it doesn't matter what you pick at the jump size. No, I wanted to know if the jump size mattered for any of the calculations. For the proofs, you do have to worry about the small jumps. It's the big jumps that matter, and then you have an extra argument. Usually in these, even for convergence in J1, you have to deal with the small jumps in a certain way. But the theorem doesn't care,
Okay.
and the definitions doesn't care.
Yeah, because of course, if you take an ensemble of these walks, the jump sizes will be a monotonically decreasing probability, right? Yeah, I mean, it's not like a bimodal map or some bimodal distribution. It's a monotonically decreasing probability of jump sizes.
Well,
Probability of a large
sure,
jump is
sure.
very small.
I mean, most of them. Yeah, I mean, there's restrictions on how many big jumps you can get, but that's actually a theorem about Cadillac spaces. What kind of jumps you can get?
Okay.
Yeah.
But it's all buried in there.
Yeah.
Okay, I think Peter had a question.
The exponent 2 is just for my example because I had this. Yeah. I could have changed my 2
Yeah.
to a 1 over alpha. Or-
Any alpha will work.
Well, it's easier. We've proved it for alpha between 0 and 1. Between 1
What
and 2.
happens if alpha is greater than 1, but still in
Between
the...
1 and 2, there's some extra calculation which I haven't done.
Okay.
Okay,
Where? Oh, you get something similar, but it'll just climb. So it won't go up and down. I wanted to give some example where you kind of had some oscillation. Sorry? No, because you get these intermediate dots. So no. I mean, but it would converge sensibly in E.
I just wanted to ask about the definition in F prime, the
Yeah.
distance. Why is it a min on the 2?
Oh, max.
Because-
Thank you.
Thank you.
It was all going so well. Thank you very much.
okay. I think we stop questions here because we need to continue with the next speaker, and she needs to be hooked up, I guess. Hongkun. Oh yes, let's thank our speaker. Okay, so I think we're ready for the next talk, that will be given by Hongkun Zhang, University of Massachusetts, and the title is Machine Learning of Dynamical Systems.
Okay. First of all, I would like to thank the organizer for inviting me here. It's really great pleasure to be here, and especially to see many old friends after 3-4 years. So it's great to be here. And on the other hand, for the past 2 days, I'm so glad to see that many people are starting working on billiards, because I have been working on billiards for the past 20 years. So I see. So before, in the very beginning, it was very isolated, but now I think there are many people working on billiards, because from billiard there are so many questions you can extend to, and especially from probability theory and so on. But anyway, and one more thing I want to mention, the main reason to come here is that because for Yan and for Mike, so especially last 2 days, there were many people talking about Yan. So, and also since Mike just came, and I want to say that for both Yan and Mike, happy birthday. And for I'll say a little bit about Mike. So Mike has been very, very good friend to me, especially for myself, because so Mike have been so friendly, and also he's very, very moderate. He's a good collaborator. I mean, because of him. So in fact, there was a year I decided to move to Houston. So I changed my job and I moved to Houston. It was a great experience there. Oh, sorry. So it was a great experience there, and I really enjoyed like every moment being there, because they have a very good dynamical system group there. But very unfortunate, because at that time I didn't know how to drive. So so in Houston, it's impossible to survive, because I was thinking to buy a house around the University Houston area, but it turns out to be like a very unfortunate, like impossible. Anyway, so but now I want to tell my dad I finally got my driver's license. So yeah. Anyway, yeah. Okay. All right. So even though Sandra was telling me, okay, so this is a talk about dynamical system probability theory, but I still want to talk a little bit about using machine learning to study dynamical system, because myself I was like really theoretical. I only work on proofs. I remember when I was a student, and Chernoff was once asking me, well, do you like to code? And I said, no, I really hate the code. I didn't know, because at that time people use C++. It was really complicated, and I have really a problem to remember all those commands. It's really difficult. But then, so what happened? Maybe I want to explain, especially since there are so many young people here. So I was really inspired by there were a few papers just around 2019. There were a few papers by Edward. Oh, maybe I'll mention the name. Edward Oates. So he wrote a great book about chaotic system, and also Brian Hunt. So he was a PhD student of Cecilia, and also there are several other people. So there were like So because those are people who wrote really, I mean, especially Edward Oates, he wrote a nice classical dynamical system book. And then I was really surprised that they wrote several papers about using reservoir computing to learn chaotic system. So I was trying to follow their paper. At that time, I didn't understand much. And then there was one time, I think it's just beginning of the COVID, there's nothing to do, and I was searching online, and I saw that Edward Oates has an introduction article on the internet, but unfortunately I cannot find it anymore. So after I read that article, it really inspired me. So maybe I'll explain. I'll try my best to explain to you what was written there. So it's basically saying, okay, like since for many years, right? So mathematicians have been very important in the society, because for example, not only many of us can solve, many of our great mathematicians can solve conjectures, but also the work that we are doing is connected to the real world. So for example, there are many data available, like related to economy, related to biology, and also related to chemistry. There are many data there, and then they want to understand how the data, what is the complex dynamical system behind those data that driven the data. Can you find a mathematical modeling to model the data such that once you understand the mathematical model and you try to do predictions and then to tell us something about the real world situation? And this is why applied mathematician was very important, and then they have the chance to cook up mathematical models, and then the pure mathematician continue with the model and then to do more fantastic work. But things change since like I think 10 years ago, because the powerful computer, especially the powerful chips, right? So there are like all these very fantastic GPUs, and so from that perspective, I mean, the computer can do parallel computing. So even though the concept of neural network has been there for like 10 years, and I was really surprised, maybe 20 years, but it became very useful only since last 10 years. So maybe I'll explain to you so what I have seen. So the main question is the following, is from the real world situation. So for example, they observe some kind of data, and what kind of data they are. Maybe I'll give you one example. Because of the COVID situation, and I remember in the middle of 2021, and even for me, I was like miserable. I don't know, okay, will it over? I mean, how long it'll take? In the beginning, in the middle of 2020, we'll say, oh, maybe it will finish, and then 2001 maybe finish, but then we don't see the hope. So, for example, this is the COVID-19, the infected people infection data set. And then one thing we can do is that, okay, so the main question is like, can we do some kind of prediction? When will the infected people, the number going down, and then we see hope everybody can go up, right? So, and turns out that even for the COVID data, I'm pretty sure, I think there are at least like 1,000 papers available for the past few years. And in fact, 20% of the paper were done by mathematicians, or maybe more than that, using the so-called SIR model. I don't know how much you know. This is SIR, or maybe some kind of extension of SIR model. Those just like 3 ODEs, some ordinary differential equations. So it turns out that, so they try to fit those data by solutions of ODEs, and then by looking at this set of differential equations, they try to do some kind of prediction. And it turns out that some of the work, and also people try to extend SIR model to more, maybe to include more variables and so on. It turns out to be that some of the work are very powerful, and at least even though it doesn't fit the model perfect well, but still can explain something, maybe also do some kind of prediction. So this is what mathematical modeling is doing in terms of data set. And on the other hand, so what does your neural network do is that, so for example, what is a neural network? It turns, even though when you look at the code, and in fact, also for me, for the first few years, I was like looking at all the papers. The paper was written mainly by computer scientists, engineers, and those are written very, like, for us, it's really hard to read, to understand. And eventually I figure out that from our perspective, neural network is really defined by functions. Those neural network for us is really defined by functions. So I'll call FNN, for example. So those are real data. The real data are generated by dynamical systems, say fx equals to y. So there is a fx equals to y. When you do mathematical modeling, you try to cook up another dynamical system such that we want to make sure that this dynamical system is kind of can be used to approximate the real dynamical system in some sense. But of course, when we do mathematical modeling, for example, the COVID data, we try to use ODEs, and that's like it's impossible, right? We know there's a lot of errors, but still we really hope that it captures the trend a little bit. So that's why how we tolerate about mathematical modelings, and then people can extend into PDEs, SDEs, and so on. And in terms of the neural network, it turns out that neural network always defined by a bunch of functions, and those functions is which I also called that learned dynamical system. And it turns out that this learned dynamical system can be also used to approximate the original underlying complex system. And it turns out that, and there's one more thing you can do, because here you just say, okay, I can predict the trend. Well, some sort of is okay, but there you can define some kind of loss function such that you can really measure the distance between the real dynamical system and also the learned one, and for some kind of norm. Of course, how do you define the norm? The norm, that is when you define the loss function such that they are kind of as small as possible. How do you know they are small? Because you want to do the training. When you do the training, you do the testing, and when the error is really small, for example, 10 to the -3, -4, and then it's satisfied, you just save your neural network, and then your neural network really defines approximating dynamical system. So this is what I learned from that article, and that also inspired me. And I was really felt scared, because it seems that after the invention of the powerful chips and GPUs, the neural network can be very, very useful, and also eventually it can be really comparable to all the mathematical modelings. And so that really inspired me, and then I decided to start to work on machine learning. So this is just my motivation. Okay, so here I will talk about three topics mainly. So the first thing I will talk about is something related. For example, how do you use machine learning to learn chaotic system? Because we're working on dynamical system. This is dynamical system group here, and so that is related to the time series forecasting. And on the other hand, of course, you can say, well, if after you learn the map, right? You learn the map. How do you know that this map can capture some mass, some underlying, for example, their environment measure, their attractors, or maybe their conservation laws? How do you know that they can capture that? And that's another topic which I'm going to present about machine learning independent conservation laws for Hamiltonian system. If you have a Hamiltonian system which is really high dimension, it has many conservation laws. Can you cook up a machine learning neural network to learn those conservation laws? And also the last one, if I have time, I will talk about perturbed Hamiltonian neural networks. Okay, so what is the main question? The main question is that so we're given the data set. So you have a data set, maybe this data set is driven by a very complex dynamical system, and which we have no idea to write down the equations. Of course, I can give you some. So even for billiard, right? For example, for billiard, and if I just draw a random shape of the billiard table, there's no way you can write down the equation of the billiard map. There's no, I mean, the billiard map is really hard to write down. So, so from that perspective, can you cook up a neural network to learn your billiard map? And then if it can learn the billiard map very well, it can generate your solution, your orbit, right? And this is one side of the story. The other side of the story is also very interesting. I think it may be interesting to some of our young audience. So this is really, the second question is really new. And I was just thinking to start, but I have a collaborator who recently wrote a paper. So what is that about? It's mainly because I was telling you, I need a neural network is behind the neural network, their functions. Really, any neural network is defined by a complex, by a dynamical system. They're driven by functions. In particularly, and how do you understand the property of this dynamical system? So my collaborator, and he is computer scientist, and he started this direction by looking at recurrent neural network. The recurrent neural network is one of the most simple network. It has very simple structures. So he started to look at some very special examples for the recurrent neural network. And then he was able to prove that this recurrent neural network defines a dynamical system such that it has some kind of limit cycle. And then he already published this paper, and it's already a piece of very nice work. And of course, when I mention about this work here in this audience, and you may say, well, it's so trivial for us. But on the other hand, I really want you to realize that this is entirely new. For example, how all kinds of neural network working, what is the underlying dynamical system, what kind of property do they have, and all these things are open, are completely open, because I don't see many pure mathematicians come to this direction. So a lot of things are open. But anyway, I will talk about the first questions. So mainly, so this is essentially what I mentioned in the beginning. So in the real world situation, you have a lot of data. So the question, but of course, you have this data, but so there are two challenges. One challenge is that you don't know how the dynamical system, we don't know the equation that's driven the data set, right? So how is this point mapped to another point? So what is this underlying equation? We have no idea. Sometimes it's multi-dimension, it's very complex. And this is one type of the problem. Another type is that sometimes for PDEs, for complex PDEs, you have equations, but on the other hand, it cannot be solved. There's no closed form solution. So people try to use numerical. That's why the numerical analysis has been there. They try to use numerical method to solve PDEs. But there's before we were okay, we try to tolerate, but now things kind of changed. So we have a much higher standard. And I will show you that in terms of one of our favorite dynamical system, the Lorenz system. I'll show you that the numerical work that you try to simulate the solution of Lorenz system is non-acceptable. That's why there is a place needed. On one hand, if the dynamical system is not known, can you cook up a neural network, try to learn the underlying dynamical system? Secondly, if your dynamical system is known, can you cook up a neural network such that it can learn much better, simulate much better the trajectories? Okay, so so those are the challenges. So the first challenge is that because there are so many neural network available there, which one do you want to choose? And secondly, is that if you have a data set, can you construct a neural network that fit your data very well? And the third one is that even though you can feed your underlying data set very well, can you learn physical laws? Can you learn the environments, for example, the conservation of energy and momentum and so on? So I will just give you one more example. So in the field, because we all know about this ChatGPT, right? The ChatGPT was driven by a very famous neural network called Transformer. So so this is also, I mean, if you look at the Transformer, and I don't know how much our audience know about Transformer. In fact, from our mathematical language, Transformer is just a special type of, they try to use this Markov chain. For me, it's just a Markov chain. They try to learn the transition probabilities from one state to another. But anyway, I mean, you don't see this interpretation, that's just mine. But anyway, so in the field of computer, for example, computer vision, or maybe natural language processing, there's no, I mean, it's really, really hard to come out mathematical formulas. You cannot, when you do prediction, for example, when you do, I mean, not prediction, you do translation, you translate from France to English, right? Or maybe Italy to English. And then there is a map, there's a map behind that, but it's hard to write down these equations. So, so the main idea of the neural network is to try to mimic the mathematical equations. And once you can find that equation, which is defined by the neural network, and then what you can do is that you can use that to do new translation. And that is really why the ChatGPT is doing much better than Google translation to do translations and also other things. Okay, so so what is the main procedure? The main procedure for learning, for machine learning of dynamical system? The first step is that we can, I mean, even though we have a big ego in mind, but we have to start with a toy model. For example, start with some toy model and use this toy model to generate some data set, and then you know what is the real underlying dynamical system is. And then you try to cook up a neural network, try to learn this data set, and then see if your neural network learn well the underlying dynamical system, and then you generate a new orbit and see if this new orbit is the same as the orbit generated by the real dynamical system. So this is mainly the first step, and that is the top for my first topic. And after you can do this, and then of course you can trust your neural network to do more complex, to learn more complex real world data set. And the second step of the procedure is that once you have learned your the underlying dynamical system, you can do further forecasting because you can generate the orbit, right? And also in the high dimension data, you can find some kind of patterns, and you can hopefully you can find conservation laws and also environment quantities. Maybe you can recover your attractors and so on. And also of course, the most ideal case is to discover the governing dynamical system equations. Can you write down the equations? And that is also possible. There are some directions in there which I didn't do, but there are directions in that. That's the right direction to go. Okay, so formulation of the problem. Because we are mathematicians, we want to understand this whole story from our perspective. So what's the formulation of the problem from mathematical point of view? It's really simple. It's just like, okay, we start with some data set xn, yn, such that xn is sent to yn by a real function, dynamical system. And then the hope is that, okay, from mathematical point of view, we try to cook up approximating function f such that f is as close as possible to the underlying f, which is defined by those observables. And of course, this question is not very accurate, because what do you mean they're close? They have to be close under some kind of matrix. So there are two things. One thing, you need to define what kind of family of dynamical system, what kind of the family of your candidate you choose to approximate that f, which is unknown, right? So this is important to choose the correct family. Secondly, how do I know that they are really close? So that means that I need to set up a distance function which define the metric such that these my two functions are as close as possible, and in terms of this distance function. And then you try to, because there are a bunch of functions here, you try to minimize the distance, try to find the optimal function that can minimize the distance between this class of functions and the real underlying function. And if you can find that, and we're done. So this is like a minimization optimization problem from mathematical point of view. And from machine learning point of view, is the following, still the same question. So now you have data set, you have the data set, and we still want to find first of all, we need to find, because the data set has a hidden dynamical system, we have no idea what that f is. So the first thing we have to decide is that we need to design a neural network. So what do I mean if I design neural network? It really means that you design neural network means that you're really trying to set up a sequence of functions, functions parameterized by some parameters. So really, any neural network is defined by a structural functions. But when you might heard about training, people say, okay, I'm training the neural network. What does training mean? Training means that you don't change the structure anymore, you just change the parameter. So for example, if I train 200 times, that means that I obtain F1, F2, F3, I obtain 200 functions. They have the same structure. So what is changing? The only thing changing is the parameter changing. So in other words, once you design a neural network, you have a family of dynamical system. And then the hope is that, okay, hopefully you can train your neural network such that you can find the ideal dynamical system which is as close as possible to the real one, as close as possible to the real data set. And if that's the case, if you can find the perfect one, I mean not the perfect, the best one, which minimize all the parameter, and then F theta star is the one. F theta star is the one we can stop. So that's when we say I trained my neural network, I finished. So when you finish training, you can always save it. You save the weight. So in other words, you saved this function. Okay, so the nice thing is that once you select a neural network, the only thing changing is the parameter. And also when you define a loss function, of course, we have to define the distance function, which is defined by a loss function. And this loss function, most of the time we take the averaging along the loss function between the real data set and the predicted data set, right? So this loss function depends on theta, is a function of theta. And then the way when I say I train the neural network, it means that you try to minimize the derivative of your loss function with respect to theta. So basically that's it. So this is what the main idea of using neural network to learn a dynamical system. So there are three most important ingredients. The first important ingredient is that you need to choose one which is a nice network structure such that this class of functions as this class of dynamical system. So in other words, your dynamical system will be somehow be here, maybe accumulating point. And that's very, very important. Even for me, I was like, oh, it seems like a mystery. Why it is true? Secondly, and once you choose your neural network, you have to choose a nice loss function, because if the loss function is not very good, maybe I'll show you some pictures.
What was the first one you said? The first criteria you said that what? Theta, how to choose the age you said?
Yeah, because there are not many neural networks. For example, I can name a few. There are recurrent neural network. There are long short term. There are different names: long short term memories, transformers. There are GANs, all kinds of neural network available there. So which one you want to choose? Once you choose one, that means that you choose your H. And then
you said there's a certain criteria for that. You just said there was something. I missed it.
So once okay. So once you choose a neural network and then when you start to train it, and then you change your seed. The seed is changing, but the structure is not changed anymore. So H is fixed, basically. So that's the first important thing. The second important thing, once you fix your network, you have to choose a correct loss function, and you have a lot of freedom here, maybe I'll show you just quick a picture about the loss function. So for example, how do you update, how do you train your neural network? Basically, I was trying to say, so I want to find a sequence of state converge to F in terms of in terms of this matrix, right? A matrix defined by my loss function. How do I know that this thing converge? So in other words, I want to make sure that the distance defined by the loss function is as small as possible, and then this is tested on your test side. How do you know that they're small? You have to train it. So the main idea of the training is called this gradient descent. All you have to do is just you take your loss function, you differentiate your loss function every step, and such that the derivative is decreasing. You can see, for example, right here is the minimal point state, and then once you find that state, you can define your F state, and then you satisfied. So this is how the perfect state is chosen. But this is the most ideal case. Most of the situation, the loss function is very complicated. For example, there are many minimal points, and for example, unfortunately, if you here got stuck and there's a global minimum right here, it's still, that's why there's a big community try to understand try to study the optimization problem for control the loss function of neural network. So there is a big set of problem here. There's another thing I want to show you is that how do you, for example, I was talking to another mathematician and he was asking me, how do you know that my limit function is in here, right? So you've chosen a neural network, what if it's not in here? And basically, no matter how much I train, this thing cannot converge, and then it's useless. But fortunately, there is a mathematical theory behind this, and this theory is called universal approximation theory. The first time I saw it, like, wow, that's amazing. I didn't know that. But on the other hand, it's really trivial. It's one of our, I think, analysis or maybe even calculus results. So, but anyway, so the work started in around 1989, but I didn't know that. And later on, I realized this. So it's approximating functions using 2 layers of neural network. So the 2 layers of neural network are the most simple one. And any other fancy neural network can do much better than the simple feed-forward neural network. This is a very, very basic one. Anything else are more complex than this, more advanced. So this is a theory which I think is much more proper, which I can show you here in this gradient. So you have a dynamical system. So say you have a continuous dynamical system which is defined by a map from domain X to domain 1. So that's your underlying F. So this function F is from X to Y, and assume that it's continuous, it's right there. So the theorem says that, okay, if you have a function, and first of all, you choose something called activation function sigma, and assume that sigma is not polynomial, because we all like polynomial. It turns out that polynomial is not good here. But anyway, as long as your peak of function set is not polynomial, and then it turns out that this neural network, the neural network which is called feed forward, a linear, you see everything is linear. So this X is your input, right? X is your input. So this W is a matrix, B is a matrix, and that W and B and C is also a matrix. So these 3 matrices define your parameter. And once you set up your parameter, and this is linear function, and the only thing non-linear is this sigma, which is called activation function. And this symbol is called Hadamard product. It's a different product. So that means that this function acting on every element of this vector. So this is a vector, right? So this guy acting on every element of the vector. Let's say, so this is the simplest neural network, which is called feed-forward neural network. And it turns out that, so the theorem says that even though this neural network is so simple, it can be used to approximate any continuous function from any side x to y. Of course, the x and y cannot be very, I mean, so for example, if I say, you say I take a counter side, definitely that's not true. It's have to be untrivial, compact side with a non-trivial interiors, have to be a good side. So so this theory has different version, but this version is my favorite. I want to show you that it's so this is really why the neural network is so powerful. The simplest one layer, and this is really a two-layer neural network can be used to approximate almost any functions, continuous functions. Doesn't matter what the dimension is. And of course, this is just a theory. But when you really cook up a neural network, maybe there's another question is that how fast is the convergence speed? How fast the convergence speed? And that also depends on your loss function. And this is why in the beginning, you think people always think, oh, that's simple. But when you really start training it, it can be really a disaster. And then there was a neural network which I trained. It's not decreasing, but instead it's increase the loss function increase. So there's some kind of tricky part there, but still you can see that the theory underlying behind it is very simple. Okay, so this is just summarize what we're going to do. So now you give me some data set, right? I want to learn the underlying dynamical system. The first thing I need to choose a neural network such that the underlying neural network is kind of a accumulating point in there. And secondly, I need to choose what the loss function is. And of course, when you choose a neural network, and there are many other things you have to choose. How many layers, for example, how many layers, what's the number of the dimension, and what is the learning rate, and so on. There are many parameters we have to deal with. But other than that, so the main difficulty thing is to choose a loss function and the neural network. And then to train it, so you can, because right now the computers are so powerful, you can train many neural networks all together simultaneously, and then you just choose the one which has the smallest test rate, and that's and you just stop there. And also another thing is that I think we're really lucky because as I was telling you, when I was a student, and I really hate coding because when I look at C++, and it's really, I have to remember all those commands, it's impossible. But it turns out that, so there's something called Python. This is a new type of language, and it turns out to be very friendly. And of course, Gary has a different story. Gary like Julia. There's another program called Julia, which is also very friendly. But I myself found that Python is much easier to learn. So if you know how to use Python, and then there are many packages, you don't have to write from scratch using TensorFlow and using PyTorch. And recently there's been JAX also invented, so you can use them. Yeah, I didn't know any language before. Just like 3 years ago, I started. I think it was okay. It's not that scary. It's very friendly. But anyway, so those are my recent work. So I have been working on. So for example, the first work started with my colleague. We start like during the COVID, right? There's nothing to do. So we have COVID data set, and I didn't like the SIR model. So what I did is that, okay, we start using a PIN because there's some parameters which is hidden. It's not, you cannot trust them. You cannot trust them. So can we cook up a neural network to learn the real, the underlying data, and also to do a prediction? And that is one kind of work. And because in the beginning, when I was just start with machine learning, I just go all around. I take anything as much as I can. And there is another direction. It's called graph neural network. Graph neural network is another. It's also very interesting. So for anyone who is really expert in Markov chains, and then you know graphs, right? So the graph neural network is also a great field, and there are a lot of open questions there. And also very recently, with my colleague, Panos Kavakidis, and also Julie, this is a new faculty in my department. We did some work using machine learning to learn conservation laws about a Hamiltonian system, and that's one of the topic for today. So, okay, so the main question, so when the first main question is that, as I was saying, okay, so there's an underlying dynamical system, and then can you try to find, cook up a neural network and then try to train such that these two dynamical system is as close as possible, And then the example I used is our favorite Lorenz system. So the moment I started this Lorenz system, and I already found, okay, there is a problem here. So this is the Lorenz system, right? Defined by the 3 ODEs, and those are 3 parameters which gave us this the butterfly attractor. But then the first problem we encounter is that how can we generate the real data? How can we generate the real data, right? And then we use 2 packages. We use 2 different simulation methods that was available in the Python package. One is using the CP's integration package, and which is built on from Lasota by Fortran. So that's very, very classical numerical method. And we also use another method, which is the round-Kuta simulation method. So we use two different methods, and we started with one initial condition, and you can see that after we simulate a while, one and here, the other method and up here. So that means that using numerical, I mean, of course, we all know why, because of the existence of a positive lambda exponent, right? So the error grows exponentially. So that also raises up a problem. So this is about x coordinate. You can see using the x coordinate, these 2 different methods, and they only match up to time 5. I mean, not even to time 5, right? After a while, they're completely different. So then the problem is that without real data, how can you learn your dynamical system? I mean, we cannot trust anyone, so I take any one of them. That's not the real solution of my Lorenz system. So so what we did is that, okay, because I work on billiards, we work on billiards. Like one trick for billiards is that instead of working on billiard flow, we work on billiard map, because billiard map has some advantage. So here we cook up this Lorenz map by taking a step size, and this become a very discrete dynamical system. And for this one, you can very easily generate a real a sequence of iterations which you can trust. Because there's no integration anymore. The problem is the integration. The integration by simulation, by numerical method has a problem. So there we were able to generate the real data, and then those are the data sets. So what we did is that we totally pick up 400 orbits. And then in this 400 orbits, and we will select part of 200 for training, 200 for training, 100 for validating, and 100 for test. So so the main neural network which we use is called the so-called long short-term memory neural network. And this long short-term memory neural network is kind of improvement for the recurrent neural network. So I'm not going to tell you much about here. So this is just the structure of how the neural network looks like. So you have input, and then also the neurons, and then they have how they are connected. But I'm pretty sure you don't like this picture. And this is much better. So this just tell you that neural network was defined by those functions. That's our dynamical system, right? So so there are like 6 functions define this neural network. So what you do is that you have input. You see the input will be x, and also there's a hidden h, which is a hidden layer. Hidden ingredient, and all other w's and u's, b's are parameters. So this neural network, even though it looks very complex, but they are defined by functions. And also, I want to tell you that even though I know that there have been people try to understand the dynamical system underlying and behind those neural networks. But for long short-term memory, there is 0 work. There have been no work has been done. So for example, if you put these equations together, what kind do they have, like limit cycle, fixed point, and all that? There's no work. I mean, as far as I know. And the only thing have been done is about some special case of RNNs. Okay, so what we did, okay, now we found we choose a neural network which we like, and on the other hand, we try to define a loss function. So to define loss function, and the most popular loss function is the so-called MIC, the mean square error, and it turns out that it doesn't work well. So what we did is that we borrow some idea from the sublet norm. So in other words, we take out different discrete differences. So if you give me a data set and I look at different, like the first order difference, second order difference, and I put all this information into my neural network, and I try to when we learn it, we want to make sure that not only the L2 norm are close, but also in the difference, the L2 norm are all close, and also how many order of difference you want to choose, and that's up to you. And so it turns out that, so this is our neural network. We designed the long short-term memory using our choice of loss function, and perform if my training data is only one orbit, and this is our loss. It's pretty good. If I train multiple orbit, and the loss, this is the train loss, this is the test loss, it's much better than any other available neural network with so the physical informed neural network is that they already they know equation. They put, even if you put the equation in, the loss is still much larger than ours. So this is the result we did, and then this is the prediction. The real one is the blue one underlying here, and the orange one is the predicted orbit. It performed very well, and we also use the same method. So this is, we also use the same method to study other chaotic system. So this is the extended standard map. This is one orbit. For standard map, it's a little bit tricky because it has the modular function. So for the modular function, sometimes it's a little bit tricky here, but still the performance was pretty good. Okay, so maybe I should okay, so another, maybe I'll finish this topic quickly, and then for another topic, I'll just mention a little bit and give you some kind of intuition. So okay, so we can do well in time series forecasting if you work hard. So that means that we can learn. So in other words, that means that the underlying the neural network that we trained, you can see that it performed very well for that 2000 iteration, for the 800 iterations. That means that the neural network is as close as the real, the function defined by the neural network is as close as the real dynamical system. So we achieve that goal. But on the other hand, how do we know that the neural network that we cook up can also capture some physical quantities, for example, attractors, well, and other things. So this is another work which I did with my collaborator about capturing independent conservation laws. So we start with a Hamiltonian system. So you have a Hamiltonian system, right? It's high dimension. So for example, this Hamiltonian system, so it's 100 dimension. For example, if it had 10 conservation laws, and you want to figure out using neural network to learn those. So what is the conservation loss? It just, for us, it's just anything constant along orbit. So we say that this function phi is a conservation law. It means that this phi is constant along any orbit, and also we assume that this constant this function is kind of smooth function. And along, so for the neighbors, they have to, the conservation laws have to be kind of close. So we call this to be conservation laws. And one nice property is that so because we are studying Hamiltonian system, it's not like billiards. Say they're all smooth. There's no singularities. And if you have a conservation law, you can take the gradient. The gradient is perpendicular to the underlying vector field. So this, okay. So the equation is defined by ODE. Even though it came from PDE, but you can always convert it into ODE. So this ODE has a vector field, which is F. So we say that this ODE has a conservation laws, means that this conservation law take the gradient is perpendicular to your vector field. And we try to find out, we try to learn those conservation laws. Okay, so what was it? So maybe I'll go further. So So our work was inspired by this paper. So this paper was published in 2022. They were trying to learn conservation laws from differential equations. So the authors are physics. They're in the physics department of MIT. So they were trying to, because they they understand the conservation laws for some concrete dynamical system very well. So so they cook up some method, and this is basically what they do. So they try to learn conservation laws, and of course, if you want to learn one, that's okay. You want to learn two, also okay. But how do you know you can learn all of them, and they all kind of independent? And so what they did is that they set up in this case, the neural network really doesn't matter, because as I was telling you, the universal approximation theory tells you, okay, you can basically pick any neural network available there. They all works. And the most tricky thing is to pick up the correct loss function. So the loss function they did is that, so they cook up a very complex loss function. So for example, they want to make sure that the thing you learned satisfy this equation, want to make sure that this eventually approximate very as small as possible. So if the gradient of this function times the vector field, this is very small, almost equal to 0, that means that this is a conservation law. That's one thing. And secondly, you also want to make sure that those conservation laws, they're kind of independent. So what they did is that they put this kind of orthogonal, they want to make sure that the gradient of the conservation laws, they're kind of perpendicular to each other. So this is the second condition they put in, and then they cook up a very complex neural network. But it turns out that this second condition is too strong. It's too strong, and even for the real physical system, it may not be true. If you have two conservation laws, the gradient may not be they may not be perpendicular. So even for the ground truth, this may not be true. So that's why when they do some the experiment, they do some kind of experiment. So there were some difficulties. So they found in that reference, sometimes they found much more conservation laws than the real system. So we started our work started from here. So what we did is that instead we used a Poisson bracket. So in fact, one of the theory we use is here. We figure out that, okay, if you have a conservation law, and that means that the conservation law and the Hamiltonian, the Poisson bracket will be equals to 0. And moreover, if you have two independent conservation laws, and then the Poisson bracket is always also equals to 0. So from that perspective, and we put this into our loss function. Maybe I'll just skip here. So in the loss function, we cook up projection operator. We try to do this defiliation. So we try to make sure that the conservation law that we learned, they have the Poisson bracket to be as small as possible. And maybe I'll just show you some pictures. So the dynamical system we considered, because I always like discrete dynamical system. So that's why we work on discrete Hamiltonian lattice system. So one lattice system, the lattice system has Hamiltonian function defined like this, and they are defined on lattices. So maybe I'll mention. So one system is called Calogero-Moser system, such that Hamiltonian is defined on a chain of lattices. And this system is completely integrable. It has it defined on n lattices. It has n independent conservation laws. And there's another one which we use. It's called Sine-Gordon system, and this one only has one conservation laws. So this I'm going to show you some pictures which we learned. So this is when you have 6 lattices. 6 lattices. The Calogero system has exactly six conservation laws, and the other system has only 1 conservation laws. You can see that we can capture them. We can capture all these conservation laws, and all others are not conserved. So the loss is much larger. So this is the case when you have 6 lattice, and we also increase the number of lattice into 8, the same thing, and so on. So from that perspective, because also we can save all this neural network. So each neural net, so this entire neural network is made of a bunch of neural networks, and each one of them, they learn 1 conservation laws. So you can see that it performed very well. Maybe I'll stop here. Thank you for your attention.
Thank you very much. Other questions still?
In the Lorenz case, what was your space of candidate functions in the Lorenz experiment for training? What is your space of functions, parameterized functions that you use to approximate your choice of the your specific choice?
For the Lorenz system, we try to the data set is just some orbit. We try to use this information to learn the underlying dynamical system. So that's the chaotic case. Are you talking about the parameters?
Well, because you said that you choose a space of f theta, parameterized f theta, right? When you say you design the neural network.
Right.
So
the
you
theta
need to-
is that when I say I change theta means that when you train the neural network, you're changing theta automatically. But we don't control it. It's just like the computer train it.
But it's out of a priori chosen space of functions. So what is your space of functions that you chose in this case?
You mean F?
Yes.
Capital F. Oh, in this case, we are using the long short-term memory, this one. We use the long short-term memory as our base neural network.
Okay, I did not fully understand because you said you choose a priori.
Right, we use
space.
exactly. So you have to choose which neural network you use. We choose the so-called long short-term memory, this neural network. Yeah.
Any last question? Well, if not, let's thank our speaker.
And now it's a great pleasure to have Marty Golubitsky.
Great. Thank you very much. And thanks to the organizing committee for organizing and to the scientific committee for asking a great bunch of speakers to come here. I think something simple is in order for just say how lucky I feel that for a number of years, both Ian and Matt were at the University of Houston, where I was at the time, and it was a terrific time for dynamics in one locale for one period of time. Thank you. Okay, today I want to speak about networks. It's something that Ian Stewart and I have been working on for the last, I don't know, 20 years. And the perspective I want to take is how does network architecture, so a network is going to be a graph, how does network architecture affect the kinds of solutions or structures that you want that you might see in systems of differential equations, coupled systems of equations. I'm going to split the talk into two parts, a small part on Hopf bifurcation. Let me get wasn't me. Terrific. I want to be able to, I'll talk about Hopf bifurcation on networks to give you an idea of what I mean. So much of what I'll talk about is sort of familiar, though some results are new. And then I want to spend 2/3 of the talk on homeostasis, which is a biological term and I hope a mathematical term. So when I get to the homeostasis part, I'll explain what I mean by homeostasis. Okay, so a network is a directed graph. We can associate to the directed graph a collection of differential equations, which we'll call admissible. And again, you'll see this, what I mean by this intuitively in a moment. As I said, Hopf bifurcation and homeostasis are the two applications. Okay, so let me review the Hopf bifurcation theorem. I assume everybody here knows what it is, but there are many versions, and I just want to point to the one that I want to use. You start with a system of differential equations and assume you have a trivial equilibrium with outloss of generality at the origin. And Hopf bifurcation occurs at lambda equals 0 when the Jacobian has a pair of simple, purely imaginary eigenvalues with all other eigenvalues off the imaginary axis. Generically, Hopf bifurcation produces a periodic branch of periodic solutions whose amplitude grows as lambda to the square root of lambda, where lambda is the bifurcation parameter. Okay, so this is what I mean by Hopf bifurcation for the moment. And now I'm going to show you a couple of examples in the context of networks. So one that goes back, certainly people were looking at this in the 1980s. You have a network with D3 symmetry on it, 3 nodes. The nodes are identical. And by meaning that the nodes are identical and the coupling or the arrows are identical, it means the associated systems of differential equations have the form f of x1 where on the first node. So this is the internal dynamics. X2 and X3 are the coupling dynamics. And similarly, X2 dot is f of X2, X3, X1. And the key is it's the same f. That's what the same node would mean. And similarly for X3 dot. So this is the collection of these systems are admissible. And if you start with a equilibrium where X1 equals X2 equals X3, and in network language, they're synchronous, in symmetry, they're invariant equilibria. Then there are, if you get Hopf bifurcation from such an equilibrium, that breaks the symmetry, then you will have 3 kinds of solutions appearing. One solution has 2 nodes oscillating in phase. Second solution has the 3 nodes a third of a period out of phase, but identical waveforms. And a third solution has 2 nodes half a period out of phase, and the third one oscillating at twice the frequency, which is to say it's a multi-rhythm. The different nodes have different frequencies. So this is a kind of thing where you can say, well, the symmetry or the network structure, take your choice, gives you certain kinds of solutions that you wouldn't expect to see in a general system. Now, here's one that Matt was involved in. I can still remember sitting around on a computer screen finding a solution to Hopf bifurcation in this network and not understanding what was going on at all. So let me explain what the curious phenomenon is. The regular network is one where all the nodes are identical. So in the admissible systems, the coordinates f are the same in all of those. In this case, each node has one input, so one coupling variable. And the admissible systems, again, in this case, x1 dot is f of x1, and it's self-coupled x1. x2 dot is f of x2, x1, and x3 dot f of x3, x2. Okay, so suppose you have an equilibrium which is synchronous. So all of the variables are equal, and it loses stability via Hopf bifurcation. What may be a little bit of a surprise, and I'm not going to do the calculation, but the Jacobian is going to be nilpotent and have multiple eigenvalues in this case. So the complex eigenvalues are not the standard ones that you would get. Okay, and what happens is that you get a solution where the first node goes to equilibrium. The second node is oscillating with some frequency, and its growth rate is the square root of lambda, just like you might expect in standard Hopf bifurcation. And the third node oscillates with the same frequency as the second, but the growth rate is lambda to the 1/6, usually bigger. And this is what was confusing Matt and me when we were doing the calculations, because it looked like it wasn't a local bifurcation. It looked like the thing was just jumping order 1. And it took a while to sort this out and to come up with proofs that this is, in fact, exactly what does happen. Okay, so this gives you a feeling that network architecture is forcing something to do with the kinds of solutions that you might expect to see. As a third example, suppose that you assume that all nodes and all arrows are different. So this is what we call inhomogeneous or fully inhomogeneous networks. So it's completely different from the regular networks that I was talking about in the first two examples. And x1 dot, you have x1, but you also have coupling from the fourth node, so it's x1, x4. X2 dot is f of, well, where's 2? 2 is up there. It gets coupling from 6, but these are different f's, f1, f2, and so on through to the 8 nodes in this network. So we have the admissible systems, the network. Is there anything unusual that happens here? Well, a little bit of graph theory. 2 nodes, I and J, are path equivalent if there's a path from node I to node J and a path from node J to node I. And there are a number of path components that can happen in a network like this. You can, in this case, you'll get 4 1, 2, 3, 4 components, and there's feed-forward structure in between from one component to the other. A component has an arrow. Component I has an arrow going to component J. If some node in component I has an arrow going to some component in node J. Okay, if you do this, then you can renumber, you can always renumber the nodes so that the Jacobian is going to be block lower triangular, and that's the feed-forward structure. So there are 4 different ways in which you can get Hopf bifurcation. That is, the critical eigenvalue can be in one of the 4 blocks of matrices. And well, what's the difference between, is there any difference that's discernible? And the answer is yes. The idea is that if the critical eigenvalue is in, let's say, the second block, then you'll get oscillation of all nodes in the second block with some frequency. And all of the nodes, all of the blocks that are downstream will also oscillate. So in this case, if 2 is the critical has the critical eigenvalues, all of the nodes in these 3 components will oscillate. The first component will not. It'll be quiescent. On the other hand, if J4 is the critical eigenvalue, then the fourth block will oscillate, but none of the original ones. So you get patterns of oscillation that are coming out because of the network structure. And this was published about a year ago with a number of us. Okay. So that was just a warm-up to say that network architecture can change the kinds of things that you see, even in structures, Hopf bifurcation, that you feel you know something about. Okay, so what's homeostasis? The typical example of homeostasis, it's a biological term. is that you have a system with some external variable. In this case, for this experiment, the horizontal axis is the external temperature, and the vertical axis is the internal body temperature of some warm-blooded mammals. And in these experiments done in the 1940s, what you see is that from approximately 15 degrees to 30 degrees, the internal body temperature is approximately constant, even though the external temperature is varying quite a bit. Is varying quite a bit. Okay, so Mike Reed, who's a mathematician at Duke, mathematical biologist, he and Fred Nyhout, a biologist down at Best, came up with a name for this structure, and they called it a chair. So I will continue this. And what it's saying is that in this experiment, if the temperature is really low, well, the mammal will die, and its temperature won't change. It'll just be the external the external environment temperature. And if the temperature is really hot, same thing is going to happen. So you can think of it as piecewise linear, where you have the body temperature equal to the external temperature, then flat, then the same thing on that side. Okay. Having grown up in the time of catastrophe theory, I tend to look at some things from that point of view. And it seems to me that instead of having a chair, really you should think of this as a homogeneous cubic, and the output is a function of the input. And that instead, how do you find something which is approximately constant? It's not so easy to come up with an algorithm that gives you this. Whereas derivative equal to 0, infinitesimal homeostasis, is something that can be tested and used in theory. So what I'm going to do for the rest of this talk is talk about infinitesimal homeostasis, where the output as a function of the input is approximately, the derivative is 0 at a point, and therefore by Taylor's theorem, it's approximately constant on a neighborhood. Now, Mike and Fred and Janet are really interested in biochemical networks, and a biochemical network, I'm not going to try to give a course in biochemistry. Besides failing miserably, it would be going off on a tangent. But let me show you a couple of examples just so that you get the idea. If this, you have a system with 3 substrates, X, Y, and Z. X will, as X varies, it changes the concentration of Y, changes the concentration of Z in a line. The G's that are going down here are flux functions, and in general in these models they're just constants. So they have to do with let's see, degradation. I knew I had it somewhere. That degrades the various chemicals. So from this point of view of networks, we can take the systems of differential equations that occur in biochemical networks, which have this form down here, and write it in what I might call a math form, or the admissible systems associated with, well, what should this network be? I claim it should just be this. And all of the nodes in this case are different. And the dynamics, the arrows are different. But this has this feed-forward structure, and it's called feed-forward excitation. So the math form of this, the admissible networks, have to have an input node, a regulatory node, and an output node. Okay, so this is one biochemical network. Another biochemical network is substrate inhibition. And again, 3 nodes, 3 substrates. But the difference is in the first network, the concentration of the first substrate affects the degradation of the last one. It modulates that. In this case, that's not true. Okay, so you can write down the admissible networks, the admissible systems associated with this network. And I trust I don't have to get a formal definition of admissible networks, that you sort of get the picture. Okay, Haldane, famous biologist, actually showed that substrate inhibition, which comes to this network, occurs in lots of biochemical networks. So this is these two things, feed-forward excitation and substrate inhibition, are different networks, but they appear around in okay. So what I want to know is, when is the output node approximately constant on variation of an input into this network? And again, in the biochemistry, it's not unreasonable to assume that there's an input from the outside world into the network through this first substrate. And one wants to know whether the output is being held approximately constant. A third network is this more complicated, but still 3-node network, which is called negative feedback. And some control theorists published on this network a decade or so ago on it. But again, you can write down the admissible networks, the admissible systems associated with this network. And I didn't write down a biochemical analog of this, just the math network in this case. So the general setup is that a network is going to have an input node, some number of regulatory nodes, not just one in biochemical networks, and one output node. I should say, networks can have more than one input node. Networks can have more than one output node. In each case, things get a lot more complicated. So I'm going to stick to, for the purpose of this talk, to what happens when you have one input and one output. And in order to talk about homeostasis, we have to have an input-output function, so that you know, as you're varying an input parameter, you can measure in principle what the output is doing. Okay, so here's the way that biochemists think of this. You can have a stable equilibrium for the admissible system associated with one of these biochemical networks. So all I'm saying is that there's some point x of there's some point I naught where you have the stable equilibrium. If I vary I, because this is stable, the equilibrium will move and remain stable. Okay, the x naught of I is then going to be the input-output map. That is the coordinate that's associated with the equilibria, the family of equilibria x of I. The last coordinate is the input-output map itself. So infinitesimal homeostasis occurs when the derivative of x naught, I should say O prime at I naught is 0, where the prime is derivative with respect to the input script I. Okay. Now, what's going to follow is the deepest part of the talk. I just want you to be prepared. I hope you've all gotten your revision of Kramer's rule in mind, and I'm going to use Kramer's rule to set up the rest of the talk. You have a admissible system. Here, I've put in all the variables in for a particular network. Not all of these variables would be present in each F, but just put it in there. And implicit differentiation with respect to the script I is going to give you the Jacobian, 3×3 Jacobian times xi prime, x rho prime, x o prime. And that's going to equal, well, putting on the other side, the derivative of f iota with respect to script I is going to be here and 0, 0. So if I want to solve for x naught prime, that's what I want to know for infinitesimal homeostasis, I just have to put this vector in third column over here, take determinants, and what happens? Well, in one case, you get the determinant of J, but we're assuming you have an equilibrium that's stable, so that determinant is has all eigenvalues which are negative. The determinant's not 0 for determinant of J. The FII, that I'm going to assume is not 0, and generically that seems like a reasonable assumption. So x naught prime is going to be 0 precisely if the determinant of this 3×3 matrix is non-zero. Or sorry, x naught prime will be 0 precisely when this determinant is 0. But here we can expand along the third column, and you get the determinant of H, where H is this 2×2 matrix. Well, in fact, it's general if you had n regulatory variables, then this would be an n+1×n+1 matrix. Okay, and infinitesimal homeostasis when the determinant of this is 0. So it means that we can construct the input-output map and compute points where the derivative is 0. Okay, so let's look at the three networks that I mentioned. Feed-forward excitation, substrate inhibition, and negative feedback. And the first one, the determinant is just of a 2×2. Now I'm assuming that things are 3×3, that we have one row and 3 variables altogether. The determinant of the feed forward is going to be just what you'd expect, the product minus the other. And let me be a little bit clearer. Each of these derivatives associated to fluxes, this is iota going to rho, rho going to O. So that's one path which goes from input to output. This is iota goes to O. That's the other path normalized by the internal dynamics of the regulatory node. So in order for this to be 0, the two have to balance each other. The flux along the two paths have to balance each other. That's one kind of infinitesimal homeostasis. The substrate inhibition has a 0 down here, because some variables were missing, so the derivative in Jacobian and then into H are 0. And so the determinant is just the product of these two. And there's two ways in which this can be 0. Either the arrow I to rho goes through 0, or the arrow rho to O goes through 0. And that's a different kind of homeostasis. And finally, the null degradation, or rather the negative feedback, leads to these two, one of these two terms being 0. FOI is saying that this arrow goes through 0, going from excitation to inhibition or vice versa. or you have F rho, X rho being 0. That is, the internal dynamics of this goes through 0. Remember, these were degradation terms that we were reading off in this way. And this is saying the degradation goes to production or vice versa. So a third way, a third kind of infinitesimal homeostasis that occurs. Okay. Those were 3 motifs. There are 13 different 3-node networks, which you can have fun writing out and making sure that you got 13 and only 13. But it's not, that's not quite right. It's also the case that you have to choose an input node and an output node. So each one of these has 6. So there are 78. Well, some of them are duplicates, but there are a lot of 3-node networks. And the question you might ask, well, we asked, was, are they all different? Are there just a gazillion of these networks? And the answer is no. If the output node, so output node down here, is not downstream from the input node, then the output won't depend on the input, and you'll have a homeostasis. The derivative will be, the thing will be constant, but it's kind of silly homeostasis. It doesn't have any biochemical meaning. So you want to assume that the network has, at least at the input node, has a path to the output node. And more than that, if you have a node that's in the middle of all of this stuff, it had better be downstream from the input node and upstream from the output node. So otherwise, the derivative will be artificially 0 in that case. And we call a network a core network if every node is downstream from the input and upstream from the output. So you can ask, how many core networks are there? Well, many fewer. And then in addition, this determinant of the Jacobian or this H matrix that I was pointing to is really a factorization of the determinant of the matrix H. And suppose that the factors are identical. Well, then the phenomena of this kind of homeostasis is going to be the same. So we want to assume not only that in a core network that downstream is nodes are downstream from the input and upstream from the output, but in classifying, want to know that the H matrices are all different. Well, theorem with Yang Yang Wang is that there are 3 classes of core equivalent 3-node networks, and they are given by feed-forward excitation, Haldane, and null degradation. So what looked like there was a horrible problem of combinatorics, even in these simple 3-node networks, turns out not to be the case. There's basically 3 types of things, and they have to do with the way fluxes go through 0 along paths. Undergraduate working with me on a research project, Joe Wang, and he took on classifying the 4-node core networks, and there are 20 of those. If you ask how many networks are there, 199. There are 12, 4 times 3 times a choice of input and output node. So several thousand input-output networks. But in terms of what these networks can do in terms of infinitesimal homeostasis, there are 20 of them. So the theory gives you something really well. So a little bit of graph theory. There's Frobenius-Koenig theory, and I'll just give you the output of the theory and not try to explain it. The homeostasis matrix H can be put in block upper triangular form. that is, there exist permutation matrices P and Q such that PHQ is block upper triangular. The determinant of PHQ is the same as the determinant of H. So if we're talking about finding infinitesimal homeostasis, you take the derivative, you take these blocks, and what you get is the determinant of H is the determinant of H1 through times the determinant of HM. Each block corresponds to a different homeostasis type. Well, mathematically, is there content in that? And I answer again, yes, and I'd like to explain why. Okay, each block of infinitesimal homeostasis corresponds to a place where the output node has derivative with respect to I to be 0. Okay, we agreed with that. So therefore, each block can have nodes. It is possible for each block to have nodes more than the output node, which have infinitesimal homeostasis. So one of the row nodes could do this. And Will Duncan, who was a student of Mike Reed, was able to prove that every homeostasis block corresponds to a unique homeostasis pattern. And let me explain what I mean by that. So let's look at the substrate inhibition. Remember, of course, you remember the calculation. It had this 2x2 form with a 0. And there were two ways in which the derivative could be 0. X row. So you could have X, the derivative of F row with respect to Xi being 0, or the derivative of X row with respect to, of FO with respect to X row being 0. In the case of the derivative of F row with respect to Xi being 0, both O and rho will be infinitesimally homeostatic. If you take FO and differentiate it with respect to X row, the other one of these, then only the O row will be infinitesimally homeostatic. And this is something that we're really interested in understanding better. Is it possible that there are that this has biological significance as well as mathematical significance? And I think it will, because this is saying that in one case, it's the same network in both cases, but in one case for homeostasis, you get the only one node being infinitesimally homeostatic, and that's the output node. And in the other case, in this case, you get 2, and in this case, you get 1. And the theorem, the general theorem of Will's was that this is true in general. All of the blocks are distinct, have distinct patterns of homeostasis. So, okay. Janet Best, Mike Reed, and Fred Nyhoot are biologists. Mike and Janet are both in the mathematics department. And Joe Wang, I mentioned, who is now a graduate student at Michigan. Fernando Antonelli in San Antonio. Ian Stewart, who has done a lot of this work together. Yang Wang, and Will Duncan. Thank you.
There are two homeostases. Like, is it less likely than the other one, or?
I don't know. the question of the biological significance of these two things, I think, has to be answered first. And so what we would like to be able to do is to find two different biochemical networks, both of which lead to, let's say, substrate inhibition, and give you the different things and say, well, in one case, you're going to see two nodes being homeostatic, and in the other, you're going to see one. It reminded me of something that I wanted to say. The mathematical definition of homeostasis is not agreed on in the literature. My favorite is an example of a paper where in the title is the word homeostasis, and nowhere in the paper does the word homeostasis appear. It's supposed to give you some idea that things are still the wild, wild west. And what we were trying to do here is to give some mathematical rigor to what's going on. And this is just the first attempt.
I was wondering if the feed forward is combined with the substrate inhibition. Is the feed forward combined with substrate inhibition? I'm coming from a biologist perspective. And is it similar to feedback?
So the networks are different.
Mm-hmm.
And one of the nice things about the theory, the classification, it gives a nice way of detecting feed forward structure versus feedback structure.
Got it.
So I didn't go into that, but yes, that's there.
In neural network, you have a homeostasis because brain, the neuron work with some level of firing. Do you think that your theory can be applied to neural circuit in which you have inhibition and excitation between the cell?
I sure hope so. I mean, I think that that homeostasis is a concept in biology that occurs in many different places. So you could have little changes, like instead of looking at the biochemical networks, what about gene regulatory networks? They have slightly different structures, slightly different answers, but the same ideas are there. Now, could this work with neuroscience? And I think so, but I can't say yes or no for sure.
Oh, hi, Marty. In the example you gave, you had the second derivative also zero, but in the networks, you only require the first derivative zero. Is there any, am I missing something there? Or to get homeostasis, you need a flat second?
Yeah, let me just repeat what I said and stop me where it gets confusing. Okay. I have one network with two ways to get infinitesimal homeostasis on the last variable, on the output. And it turns out that if one of these derivatives is zero, this flux goes from excitation to inhibition, say, I would get, if I get it right, this one. So I would have both the the regulatory node and the output node being infinitesimally homeostatic.
Okay.
In that case, whereas if the other one is zero, then only the output node is infinitesimally homeostatic. Okay.
Thanks.
I should say something. Yeah, I wanted to allude to that question about the neurons, right? Yeah. And there you have not just equilibrium behavior, right? Because the homeostasis happens while the neurons are spiking. And so does your theory extend to some situations where the dynamics is complicated?
Yeah, so Martin brings up a good point in this, that the crucial idea here from a biological point of view, or translating from biology to mathematics, is to be able to say what the input-output function is. In this case, we could do it, there was an equilibrium which we could trace on perturbation and trace one coordinate, and that was the input-output. You would need to know what that is in a neuroscience application. And it could be something very similar, or it could be something different. Is that?
I think so.
Yeah.
It was a great pleasure to have Gemunu Gunaratne here.
Okay. Yeah, first things first. Happy birthday to Ian and Matt. And I've really enjoyed your friendship for the last 30 plus years, I guess. Thank you. And the second point I want to make is that this stuff is relatively new and I don't have any proofs. I don't mind the proof itself, but I don't know what the limitations are. So please keep that in mind. So the work is done with my colleague, Jason Schulman, who's at the University of Houston, and a colleague, Greg Roman, who's doing experiments on Drosophila, and he's at the University of Mississippi. Okay, so let me motivate the problem here. Okay, so this is a schematic of one of our cells. And so what's happening is there's okay, cell has a nucleus which contains the genome, one copy from your father, one copy from your mother. And there are machines that read pieces of the genome and okay, produce RNA. And this RNA goes through like some simplifications, but yeah, but once it becomes a messenger RNA, and the messenger RNA then comes out of the cell nucleus. And the next step then is that like these messenger RNAs are what is called translated to proteins, which primarily do the body work in your body. Now, the complication is that these things talk to each other. And that leads to ends up giving complicated networks. I also have to talk about measurements. So okay, due to microarray techniques and sequencing, you can get the levels of the messenger RNAs within cells. Okay, but to get the levels of proteins, you can get levels of individual proteins, but not of the whole thing collectively. So the data that's reasonable to look at is these messenger RNA levels, which can be got from a sequencing experiment. Okay, here I'm showing you what's called a transcriptional network in E. coli. And this is from the text by Yuri Alon from a few years ago. What he's showing here is genes that are in this particular transcriptional network and interactions between genes. So there's like these nodes here are genes, and the links are interactions between the genes. Okay, however, the interactions are not direct. The genes don't talk to each other. Often what happens is one of these genes might produce a protein, and the protein might act on another gene. All this is to say that the interactions here are very complicated. And okay, we have no idea what these interactions, accurate form of what these interactions are. Okay, the problem I'm thinking about is the following. Okay, can you design an algorithm, like for example, to take a state with a disease, diabetes or something like that? Okay, and can you design a therapy to cure that, bring it back to a normal state? Can you do that? The problems, of course, are we don't know, we don't have a good model of what these networks are, like I said. And so whatever you try to do, we'll have to have a model-free approach. mean, you can use data, but you cannot use a model. The models would be, okay, you just cannot write a good model for these things. So you have undesirable state, maybe a state with a disease. And what you want to try to do is to get it to a target state, which would be a disease-free state. And okay, maybe you don't have to get exactly to 1 point, but some neighborhood of that region will be good, because the gene expressions of perfectly healthy people, they're not the same. They are in some neighborhood. So all you want to do is to try to get close to the desirable state. Is the problem clear? Okay, so can you do this? This is really the question, and this is what I'm trying to get at in the end. Okay, I'm going to start with something which I'm going to refer to as network modulation. Okay, so the question I'm asking here is, okay, let's take, two nodes in this gene network, or this transcriptional network, and I'm going to isolate them. Oops. Ooh. Yeah, I'm going to isolate them. And okay, if I take them out of the network, what would happen to them? So what I'm going to ask is, okay, so there will be an interaction between these two things in isolation. How does that compare with what happens to that same interaction, okay, but when placed in a network? Okay, so how do I ask this question right now? I mean, all I know in a network like this is if I change one of these things, the equilibrium will change, and the others, like in the new equilibrium, the other one would change a little bit. That's what I know. So I have to somehow use that. Okay, so here you have to resort to modeling. And the modeling, so I'm taking the interaction between these two nodes as like a Hill function, a sigmoidal function, and multiply by the levels of the other, the second node. It's a standard form that people use. So for the network, then I will have to have like a bunch of equations which do the same thing. So for the nth node, it will decay in time. These genes decay in time. And then plus there are interactions between, okay, whatever the other nodes are. And on top of that, there's an external input. In my case, the external input comes from the genome being read and genes being produced. So that is this one. Now, it's easier to think of this. If I want to ask myself if there's a solution P0, state P0, which I want to be the stable solution, I can write this external input in terms of that state. I guess that's the same thing. That actually helps like to use the eigenvalues that I want. Ian is not going to like eigenvalues, but so trick then is the following. Like I ask myself, like I take the equilibrium of this network and I change the level of one of, I'm forcing the level of this one to be a different value, and I'm asking what happens to the network. Okay, everything would change now. Again, remember, I'm not looking at a different solution of the network, but I'm changing the system itself because I'm changing this, like the level of this one node. So I can solve for the equilibrium and then, okay, go through my numerical methods and solve it, and then to calculate how much change there was. Okay, now I want to, so again, like I said, it's not a change in the solution, but the solution changes because the system itself changes. Okay, so if I take a surface like this with a very simple equation, okay, the solution is 0, 0, the minimum solution. Okay, but if I force x2 to be something else, in this case 0.5, okay, my minimum of x1 is not at 0 anymore. Like the minimum change because I forced something else on the system. Okay, so okay, how do I measure the ratio of these two things? Okay, here's one measure I can use. I can ask for the partial derivative within the network. I can compare it with the partial derivative of the change that happens here. Okay, so I want to ask myself, if I change xk, how would xn change? But I want some restriction on that. And one possible restriction is to say the interaction doesn't change. So if I change this thing, the interaction will generally change, but I'm asking, okay, how would xn have to change, like to make sure the interaction is unchanged? So that's the quantity that I'm going to call network modulation. And that then will tell me, okay, what the effect of having the network is on this one interaction. Okay, so here are the interesting results. If I take a network and calculate this modulation, it's actually very, very small. And so this thing is, here is 0.01. So what the network is doing is each of these interactions, placing in the network, it sort of modulates the effect of one on the other, and not by a small amount. So that's the primary result here. Then that the network kind of compensates for how change in one would affect another, and I'll talk more about that later. Coming back to Marty's talk, Marty was talking about the homeostasis. Okay, where some variable, one of the variables compared to other. He was looking at the external variables, but I'm talking about the expression of a gene. In that context, it'll be the expression of another gene, or a phenotype would not change with changes in this gene. Okay, so by and large, that seems to be approximately happening to all the genes. And I don't need to tune anything. This is a property of the network. And it turns out actually stability. Let me point that out. So here what I'm doing is, I'm trying to characterize this, this network here, the modulation. Turns out that rather than taking averages or standard deviations, okay, if I look at the density of things that are small here, that characterizes things very well. So this is after testing many things. So what I'm doing is to look at the, in this case, I'm looking at 10% level. So that's here. And I'm asking, okay, how many interactions were reduced by at least a factor of 10 in this network? Okay, and I'm plotting that versus the stability of the network, meaning the eigenvalue. Again, Ian, this is what it is. So the eigenvalue itself doesn't mean much if you think about it. You have a differential equation, like the eigenvalue, this negative eigenvalue, values tell you how much smaller it'll become in time. Okay, but that this depends on the time measurement. So instead of using seconds, if you use minutes, eigenvalues are going to be different. In other words, eigenvalues have to be scaled with something. And in this problem, what I'm doing is to scale it with the range of eigenvalues in this problem. Okay, and once you do that, okay, as your network becomes more stable, meaning when the largest eigenvalue becomes smaller and smaller, okay, more and more of the modulations get to this small value. And it's not only that, okay, I have used a range of different models. So I have used all-to-all coupling here. Okay, so I have used some number of networks and coupled everything to everything. I have used hierarchical networks with different types of interactions. All of them do this. Okay, so here this red one is for a all-to-all network with a Hill coefficient of 2, which means the transition from the lowest to the highest is somewhat slow. Okay, the curve then behaves like this. Okay, if I increase the change from the low to the high region, that by increasing what's called the Hill coefficient, like it looks like that. If you look at a hierarchical model, like it's even faster. And this black one is a hierarchical model with Lotka-Volterra interactions. Anyway, the point is all of them, as you make the network more stable, meaning that the largest eigenvalue, if you reduce the eigenvalue, more and more of the modulations become very small, which means the interactions are, like the effect of the interactions is reduced by the network. Okay, what is, how is this useful? So let's think about it. Like I'm changing this one node. Okay, what I have told you is that every other node changes by a very small amount, right? Okay, so it might look like this blue curve here. Okay, but the fact that it changes only a little bit means that I can get a good approximation with a line. It's not exact, but okay, it's an approximation. Okay, the nice thing about a line, okay, is that like with 2 points, you can define it, right? So like if you go to a genetic network now, I can take a wild type. I can take the normal cell. Somebody can do a sequencing experiment and get the level of every relevant gene here. Okay, now you can do a mutation experiment, and once again do sequencing and get one more point. And once you have these 2 points, you have an approximation for what's happening in this entire region. Okay, that is for every other relevant gene, right? Okay, so it's not a line in one dimension, it's in this very high dimensional space. So every other gene does this. Okay, what does that mean? That means if I have another mutant, like whose X value was here, I can tell you what all the other genes in that network are doing, right? So that's what the power of this approximation is. Of course, it's approximate, but at least approximately this can be done. Okay, there's an interesting example here, which people can do. Like, is not to look at changing one gene. Okay, so what's happening here is you have the mutant and the entire whatever changes you make in that is like along this line. But let's think of making another mutant, a different mutation. Okay, there's going to end up being another line. Okay, but now all changes like in these 2 genes are on a plane now. So, okay, so you can predict things, like for example, about a double knockout where you mutate both these genes. So all you have to do is to find what linear combination of this is in terms of 2 of them. And then once you get that, okay, you can check your prediction for every other gene. This is right. Okay, so here's when I talked to my colleague and he said he can do an experiment with the sleep deprivation network of Drosophila. And he found 7 genes that were in this network, which he knew to be in this network. Okay, and he did experiments. The experiments were to look at the wild type. Okay, and he goes through and looks at these 2 genes, these 7 genes. Then he looks at one of the knockouts, one of the single knockouts, just the experiment again, and so on. Okay, so he also found the data for these 2 double knockouts. Okay, so now I have my data. And so what I can do is do this picture. I look at the wild type and these 2 single knockouts. I can use them to predict the double knockout. Same with this other knockout. Okay, so how does this work? So again, I mean, I could in principle use, okay, 2 of these genes, let's say SDC and SAFB to get the lambda 1 and lambda 2. Okay, but remember, these are gene expression levels. There's a lot of noise. So I would like to get a few more data points, so get a few more genes to actually calculate lambda 1 and lambda 2. Like I cannot use too much because I only have 7 genes to work with. So what I have done is to use the level of 3 genes, SDC, SAFB, and this other one. So I'm trying to solve for 2 numbers using so get 3 values in each this case. So it's overdetermined. Okay, but now I can use the Penrose-Moore index inverse to get the best possible value. So that's what I'm doing to reduce the noise in this data. Okay, so what do I do now? I start with this, like this data. So I can do a bootstrap method. Bootstrap method means I start with the data I have. Okay, I look at that, all that data, okay, and then replace one of the values that I have with a like with one from the distribution that I know, because I know the mean and standard deviation of each of these things, and replace, okay, percentage 1 over E, okay, from the distribution. Right, so that's the standard way. That way you get a second set of synthetic data now, not the original data, but so synthetic data. Okay, and you do the calculation exactly like you did here with the new data set, and you go on doing this to get the distribution that you want. So that will give you the distribution. Okay, in this case, like this other gene here, the Brahma. Okay, and the values on this distribution is in this curve here. This is for 100,000 experiments like that. And the experimental data, on the other hand, is right here. Okay, so which is to say that the predictions, okay, using this bootstrap methods, like, are very good. All of the genes work out right. So, okay, so once again, what I did was to calculate the lambda 1 and lambda 2 using 3 genes, and I can make predictions for 4 other genes. All of it work out right. Not only the means are right and almost right in the middle, but even everything else is within like sort of statistical error of these distributions. Okay, so that actually worked out right. And then we went and looked at some other data. So this is not data that like we made, but this is data from some old papers. So Covert et al. Had looked at the oxygen deprivation network of E. coli. This is to say E. coli, if you put them in an oxygen reduced environment, that there's a network that's activated, and that's called the oxygen deprivation network. Unfortunately, it's only recently that people have started giving lists of genes in this network. So there's 5 of them which were known to be in this network. Yeah, and they got 5 single knockouts and 1 double knockout. Okay, and we had data for that. There were 7,000 genes that they had that they gave results for. Okay, so once again, we are trying this. Okay, so now we are looking at, so okay, since the double knockout is that, I can look at the single knockouts for these 2 ones, like to define this plane, and then okay, and see if everything else is in the plane. Okay, the problem we are having right now is we don't know what genes are in this network. So one thing we did at this point was to look at what's called the gene ontology classification. So, okay, what they have is a classification that take the known genes and classify them according to behavior and things like that. So all we could all we could do right now is to look to see if all these 5 genes are in any of these classification groups. We have found one group which contained all these 5. So now we looked at that group and assumed that that was had to do with the oxygen deprivation network. So altogether there were 284 genes. Okay, once we check this thing, it ends up about 2/3 of the predictions come out right. Okay, we could do something like even less interesting, but I'm not going to go through that part. Okay, so it looks from experimental data like this linearity does actually work. Changes are small, therefore you can approximate by a linear function. How can we use this? So okay, I'm going to illustrate this with an example, which is actually illustrates the point pretty well. So let's see you had a table and you had a silk tablecloth. Again, I want to put this tablecloth in another table. Okay, how do I do this? So okay, think about the modulation. If I raise the thing from one point, nothing else is going to change. That's why the silk was important, right? So if I lift my tablecloth from that point, the neighbors would lift a little bit, and their neighbors would lift even less. Okay, does this mean that I have to lift from every point to get the tablecloth out? Actually, no. Actually, if we hold from the 4 ends and lift it, so you can lift the whole entire tablecloth, and now I can go and put it on the other table. So what I have here is 4 control nodes, and if I control them, okay, I should be able to move this like this tablecloth. And the idea is to do the same thing for the networks. So okay, one thing you note from this example is that the control nodes really have to be far from each other. Okay, if I have lift from 4 points here, I won't lift the table. Okay, they should be very far from each other as well. Okay, so that again will come in handy. Okay, so what do? I have a network like that. Okay, the first thing is to select a node to move. Okay, so I pick one node here. Again, I can do a mutation. I can look for a mutant of that node, and then I see how everything else moves. Okay, think about the tablecloth now. Now I want, so okay, the first thing is if my target point is near to this line, I'm done. All I need to do is to change this node like to here, and then I get close to the target. Okay, very likely this won't happen. So I need to make to control another node as well. Okay, how do I find this node? Okay, think about the tablecloth. Like you have to look at things which, so get some like another node that didn't move at all. So by looking at these 2 points, you'll look for nodes that didn't move very much at all. Okay, that would be the analog of a place that's far from the original point. Okay, so that gives me a second node then. Okay, now I see if that works. So like I'm controlling 2 nodes now. And can I control it in such a way that all the points associated with changing these 2 nodes will be on a plane? Is my target point close to the plane? If it is done, if it is close, I'm done. I know exactly how to change x1 and x2 to get to this point. If not, okay, you find the third control node, right? Again, it should be far from both these nodes. So again, meaning under both these mutations, it shouldn't change. Yeah, and it doesn't have to be unique. I look at all the genes that didn't change, and I can pick any one of them. So okay, here are some observations. I'll tell you what the experiment is. So what we know is as we increase the number of control nodes, it very quickly, the Euclidean distance comes down very quickly to about 15%. Yeah, and after that, it doesn't change very much. Okay, so that's an observation from an experiment, which I'm going to tell you. So I mean, what you see here then is that you can get close to the point where you want to get to. Again, this is the Euclidean distance. And if the Euclidean distance is 0, that means every gene has reached the levels that you want it to. Of course, that won't happen, but you can get close. And so just think about this a little bit. To illustrate this point, okay, let's take a couple of equations, or so get 2-node system like this. Okay, so I'm solving for this. Okay, I'm looking for the equilibrium of this point. Maybe it's this green point. Okay, now I have to, okay, in the spirit of the entire thing, I can change x1 externally. I can force x1 to be a different value. Okay, in that case, this equation is not relevant. You have only one equation. Okay, and the solution is what I'm drawing with this red line. Okay. On the other hand, maybe I want to change x2. Okay, and look for what happens to x1, and that's this blue line. Okay, so now let's see what happens. Okay, in this system, I start with like my original state. Yeah, and I externally change x1. Okay, maybe the effect of a mutation or something like that. So the system has moved here. Okay. Okay, now if I knew that x1 was the gene that I had to move, of course I could move it back here and be cured. Okay, suppose I didn't know that. So in which case, I'm going to change x2 externally. Okay, but that will bring me to another line like that. Again, I can get close to the starting point. It won't be exactly this, yeah, but it'll get close. So rather than being very far off, which is the disease state, okay, you can come to a stage which is close to the starting point, which might be a much better state to be in. Okay, so that's what this algorithm is doing, and that's why this the Euclidean distance comes down with the addition of control nodes. Okay, so here's the experiment that we did. Right now we have, okay, we are just starting the biology experiment, which I will talk about briefly. Okay, but this experiment is one for electronic circuits, which Jason Schulman did. Okay, the circuit itself looks like that. Okay, and these elements are nonlinear elements, they're transistors. And the response looks like this. Okay, so it looks something like a Hill function, but yeah, okay, but we don't know what it is. Okay, and the network that we designed was a hierarchical network like this. So the question then is, can we use our control algorithm for to control this network? Here, the actual experiment is very simple. It's here. Okay, but what allowed us to do the experiment, okay, was we could say buy a circuit board which would measure the potentials of 20 nodes. So the node potentials here is like the gene expression levels. Yeah, and the circuit elements like the transistors are like the interaction. So that's what the correspondence is. And so it's like we start with some state. Let me just go back here. Okay, so here we start with some state, okay, and then so we get a target state by like in this case, what we mostly did was to ground 2 nodes. Okay, so the external thing that we did was to ground 2 nodes, which is to say that the node potentials were 0. Okay, now we go back to the starting point and ask, can we get to that target state by controlling the other nodes? Okay, it turns out we can do that. Okay, so okay, we've tried about 100 cases, and okay, every time it worked. worked right. Yeah, and the other thing is, if our target state, like in our target state, if you control two nodes, so if you grounded two nodes, like what happened was this, okay, thing would come down after two control nodes, right? If our target state had three control nodes, okay, we have to go through three nodes to get to this low value. And so get that again, like was what I was trying to illustrate here in this example. Okay, the other thing is, so you can ask if this linear, like, or the planar approximation is good enough. The nice thing about the electrical circuit is we can actually calculate the entire surface. That's this yellow surface here. So one thing to ask is, okay, so we have this experimental surface and the approximation with, so get three states. Okay, we could get three more states here and do a quadratic approximation. And okay, how good is this compared with that? I mean, being the electrical circuit, like it's unlike a biology experiment, we could do this very quickly and do all these things. Okay, so here's what happens. Okay, the mean potential for all the nodes is about 5 volts. So okay, that's a number that you can compare everything else with. The difference between the plane and the actual surface is like it's about 150 millivolts, which is the difference is about 3%, right? Okay, but if you do a quadratic approximation, it's much better. It's about a factor of 6 better. Okay, okay, but of course, I mean, like I already said, the gene expression levels, of course, have a lot of noise. Okay, so what happens if I add noise to this? If I add 5% noise, the differences are like that. If I add 10% noise, the differences are almost the same. Okay, so there's no need to do this higher order approximation. Like this low order approximation is already good, given that there's noise. Okay. Yeah, so the experiment that we are started and doing right now is an experiment on alcohol tolerance in Drosophila. Again, my colleague Greg Roman is doing this experiment. Okay, so the experiment is the following. Okay, if, well, Drosophila are like humans. So okay, if you give them alcohol, which is through rotten fruit, okay, they take a certain intake, okay, and after a while they fall down. Like I can't walk. Oh, okay, but if these guys, like if you give them alcohol again and do this again, after a few times, they adapt to it. Okay, and the same amount of alcohol will not have any effect on them. Okay, so that's a good thing, but the bad thing is then they take more alcohol. Okay, just like us, right? So okay, the question we are asking then is this tolerance state. Can we take this tolerance state and reverse the tolerance state back to a non-tolerant state? So actually, my colleague has done a lot of studies on this, and they have identified one gene, which is called DUNC13, and there are like homologs on it in mice, which is called MUNC13. But okay, so that's our starting point. And what they have done is to start with a, okay, so the red thing is the normal animal. Okay, so this one, like I'm just schematically drawing this. Okay, this blue one is a tolerant animal. Okay, meaning it's got used to alcohol. Okay, but now you take the mutant here. Okay, and let the guy drink too. So okay, that's the tolerance state of the mutant. So what we know from data is that the Euclidean distance between these 2 points is about 50% of the Euclidean, 60% of the Euclidean distance between these 2 points. So already by controlling this one gene, so okay, you moved away from tolerance is less anyway. Okay, but the algorithm, you go through the algorithm and ask which genes didn't change very much, and we have identified the algorithm identify what's called a long non-coding RNA, which actually has to do with alcohol usage. And so that's the next experiment we have to do. So look for the second control node, and that's what this is. And the experiments are being done right now. It'll probably take a few months for us to get results for that, because once you have a mutant, the standard is that you let them evolve for 10 generations before you do an experiment to make sure everything is stable. So that's what's being done now. Okay. Okay, so to recap, I started with this idea of modulation, which is to say that the network modulates, having a network modulates the interactions between nodes. And that leads to this idea of the response manifolds essentially being linear. And yeah, and the changes, of course, depend on the stability of the network. But once you do that, once you have this result, you can actually use it to develop or design like model-free control algorithm. All of it depends only on data and not on the models. And there are some publications. Thank you for your attention. It was very different from the rest of the conference. Okay.
Ignorant question.
Yeah.
Is a tacit approximate or assumption that you're making is that a network immediately responds? So you make these mutations and you're mutant 1, mutant 2, and then you have the double knockout.
Yeah,
So
no, so that's what happened with the electronic circuit, the electrical circuit.
But in the biology, like, is that an assumption you're making? And if that is an assumption you're making, is that biologically relevant? Because I would think there should be some delays and you have no idea what's going to happen later.
Right, so that's right. Like in the experiments, they make these mutants, okay, and they let it evolve for 10 generations before they do the experiments. Yeah, so that takes at least a couple of months to do that. And that's what the delay in the experiment is. So for the experiments, it takes some time to do all these things. And I mean, once I have the results for the second mutant, okay, then I can tell him what the third mutant has to be. Again, then he has to do the experiments again. So, I mean, right now it takes time to do the animal experiments. If this works, we are going to we are planning to do it on mice as well. I mean, mice would take even longer because it's about 10 generations each time. We tell them, yeah.
We'll have more time to get drunk then.
Yeah, that's right. Yeah, the nice thing is that if the experiment doesn't work, you drink the alcohol, right?
Let's thank Gunaratne and all the speakers today.